Good evening, Mr. Wade.
Yes, sir.
Good evening, sir. Good evening. Yes, you can probably wait another 2 minutes. I'm sending a reminder in the channel.
Good afternoon.
Good evening, students. Mr. Wade, um, I'm going to. You like to record now? To record, sir.
Yes, recording also streaming on YouTube, so you can also go back and watch that.
Recording in progress.
Alright, are we seeing my screen?
Yes, sir.
Alright.
Yes, sir. Yes, sir.
Alright, great. So I've compiled a list of topics that I plan to go through for tonight. So as you can see, I have a list that I'm gonna go through, and then I have this basic stuff. So I'm starting off with the basic stuff. There's a question in the chat. If you have a good SBA grade on paper 2, okay. So you can rely on SBA and paper 1 to pass. Make sure you do well on paper 2. Right? Thanks for that, Rihanna. I think I need to just change this over now. Alright, so we should be seeing now. So we're starting with the basic stuff. So this is from a 2012 paper. And of course I'll give you a chance to answer. Remember, you're the ones that we're supposed to be studying, and I'll assist where possible. Alright, so this is 2012 paper, question 2, and it asks us to complete the table. So physical quantities, these are the foundational things you need to know. So question 2, let's see if I can fill the scene. So we have the physical quantity area and the derived units. What is the derived unit for area? Alright, I'm seeing the chat meter square. Alright, you just earned your first marks. So it's meter squared. And what about volume? Alright, meter cube. We're on a roll. Alright, now it asks you to list the quantity that this represents. What is that representing? So it's kilogram per meter cube, otherwise written as kilogram meter -3. So if you know the quantity for each unit, you can figure out the formula. So kilogram is mass divided by m cube, which you just did is volume. So mass divided by volume gives us the quantity of density. So you were correct. So the quantity here is density. Nice. Alright, full mark so far. Alright, so in this, now you're going to state two fundamental quantities and their corresponding SI units. So we're looking at fundamental quantities now. So let's put in the chat a fundamental quantity and the SI unit. Alright, so I'm seeing time. So time is a fundamental quantity and the SI unit is seconds. Great. And I'm seeing length. Yes, length. Length is a fundamental quantity and its SI unit is the meter. Common. So it's common M for this and common S for that. And we're seeing Kelvin, we're seeing mass. Alright, wonderful. Alright, on to some calculation now. So it says here you are to calculate the density of gasoline, which occupies 150 cm cube of space and has a mass of 102 grams. So we're at B now. So first we need to identify what they have given to us. So can you identify what the question has given, what quantities the question have given us? Alright, volume and mass. So we have the volume here. So this is the volume in centimeter cube. And we have the mass. right? The mass which is in grams, right? So we are to calculate the density of the gasoline. So we're going to use the same formula for density that we mentioned earlier. So density is mass divided by volume, right? So there are two ways you could do this. You could convert your centimeter cube to meter cube and your grams to kilograms, right? Or they didn't specify in this, but that's a rule of thumb, but I'm not going to convert for now. So we're going to use the mass, which is 102 grams, and we're going to divide that by the volume, which is 150. So we're going to work it out both ways. So 150 cm cube, right? So the answer for this would be what? So let's do that in a calculator. See if I can get up my scientific calculator. See if I can find it back.
Good night, sir. Sorry for coming in late. What topic are we doing now?
We're just at the basics. So you're still early.
Okay then.
So we are currently working out this question on density. So you can try put that in your calculator and tell me what you get. I'm trying to find out my calculator I had used. So I'm seeing 0.68. 0.68, alright. Trusting you. 0.68, alright, nice. So the answer is, for the density here, is 0.68, but that is wrong. Something is missing. What's missing?
Your unit.
Yes, your units. So it's very important that you add your units, because if you don't add the units, you lose that 1 mark for the answer. So what should be the units be?
Grams per centimeter.
Alright, so this would be grams per centimeter cube. What would be this answer in kilogram per meter cube? What would be the answer here?
Sir, would it be 680 kilograms per centimeters cube?
Yes, exactly. So what you can do, you can convert these. So 102 grams to kilogram would be how much?
I got 0.102.
So the correct answer is 680 kilogram per meter cube. But we're gonna do the working out here. So 102 grams to kilogram, what's that?
$102,000.
So when we convert from grams to kilograms, are we going from a small to a large or a large to a small?
Small to a large.
Alright, so when we go from small to large, what should we do? Is it multiply or divide? Which one?
Divide?
Yes, you should divide. So a small unit to a large unit, you divide. So it's going to be 102 divided by 1,000, because it takes us 3 jumps to get to kilo. So it would be, what would be the answer? 0.102 kilogram. Alright. And for the 150 centimeter cube, how would we convert that?
Would it be to multiply 150 times 10 times 100?
Divide it.
Or is divide?
So let's identify where we're coming from, where we're going. So we want to move from a small unit to, is this large or smaller?
Larger.
So we're getting from small to large again, right? So what we should do?
Would you divide?
should be divide, right? And this should be cube, not squared, sorry. It is cube. Alright, so we know that it takes 100 centimeter to give us 1 meter, correct? We know that already.
Yeah.
So if we want to get this into cube, we have to actually cube both sides in order to get the conversion factor, right? So 100 cubed would be how much?
A million.
So it would be a million. So it's 1, 2, 3, 4, 5, 6 zeros. Centimeter cube is equal to 1 squared is, well, 1 meter cube is.
Excuse me, sir.
Mm-hmm.
For 100 square, I'm getting 10,000. Hold on.
10,000? Can't be 10,000. It's cubed. It's cubed. We are dealing with volume. It's cubed. So multiply it again one more time. So we would get 1 meter cube, right? So that's our conversion factor. So if we are to change 150 centimeter cube into meter cube, then we would divide 150 by that value. Tell me how much I got. 1, 2, 3, 4, 5, 6.
Zero point zero zero zero
0.00. How many zeros?
3.
1, 5. Right? So when we divide that, 0.00015 meter cube. So I put that in the calculator now and tell me what the answer is.
680.
680, right? Alright, so the reason I did this is because they didn't specify in the question that they want their answer in kilogram per meter cube. They didn't specify. So it gave us a leeway to use the regular units, but the rule of thumb is that you use SI units when you're dealing with calculations in physics, right? But anyway you will do it, you would still get the answer here. So but my recommendation is to use the rule of thumb, making sure your answers are in SI units. And the reason I did this first and then did the other one is to show you the conversion. Alright, so that's very important for the rest of the session. Alright, moving on. So it says here, if we have 325 grams of mercury, right? So this is mass, and the density of the mercury is 13.6 grams per centimeter cube. So what is this? This is density. Occupies a certain space, determine the volume of the space. Alright, what would we use here?
Use the density formula, but substitute.
Alright, so we're using the density formula. Let me just plug in my computer. Plug back in my computer before it dies on me. That would be a tragedy. Alright, so its density is equal to mass divided by volume. What are we asked to calculate?
Volume.
We're asked to calculate the volume, right? So we're going to transpose the equation by doing what?
You input the values in first.
You can put the values in first, yes, that's possible. Or
And then we would
By itself.
alright, so I'm going to do it both ways. So you can transpose the equation by multiplying each side by volume.
to get volume by itself.
Right. Alright. Multiply each side by volume, right? And then you would divide both sides by density, right? And now volume is by itself, and that's a long way. Now, whenever you have the unknown in the denominator, I'm going to show you a shortcut. If the unknown is in the denominator, what you can do is just switch places here. Once you switch places, then you'll get the actual equation. So this way here is the long way. The easier way is to just switch the denominator with the numerator. Alright, so let's go back. So the density is mass divided by volume. I'm going to switch places because I want to find volume. So volume is equal to mass divided by the density. Alright, do we all get that?
Yes, sir.
Yes, sir.
Alright, so volume is going to be equal to, what's the mass again?
3.3.
Again, the mass is in grams. How would we convert this to kilograms?
Divided by 1,000.
So divide that by 1,000 and we get what? 0.325 kilograms divided by, what's the density?
13.9.
Alright, what would that be in kilogram per meter cube?
Would it be 13.6 divided by 1,000?
Alright, so 13.6 grams per centimeter cube to kilograms. That would give us, you divided it?
Yes, sir.
Yes, sir.
Alright, so in this scenario here, we're going from a small to a large here. So the actual answer would be 1,300 and so 13,600 kilogram per meter cube. So that's the actual answer. Alright, when we divide this, what did you get?
Sir, but grams is smaller than kilograms. Wouldn't it be a smaller number you get?
Alright, let's work it out. So you have 13.6 grams, right? And that's per centimeter cube, right? Now our aim is to get rid of the grams, right?
Yes, sir.
So how many kilograms it takes to make a gram?
I know 1,000 grams make a kilogram.
Alright, so 1,000 grams make a kilogram, right? So I can put 1 kilogram, since it's kilogram that I want in the numerator, divide that by 1,000 grams, right? And that would cancel out the grams, right?
Yes, sir.
Alright, then the bottom part now, we want to get rid of the centimeter cube, correct?
Yes, sir.
So how many centimeter cubes give us 1 gram? 1 meter cube, sorry.
100.
100 centimeter cube,
1,000.
not 1,000. We just did it up here. We just did it over here. See there?
1 minute.
Right?
Okay.
Alright, so we want to get meter cube in the denominator, correct? So we want to get meter cube in the denominator. So we want this to be in the numerator, which is the 1 million. 1, 2, 3, 4, 5, 6. And that's centimeter cube. So when we do the cancellations now, watch what happens. So the grams here is going to cancel out the grams here, correct?
Yes, sir.
The centimeter cube here is going to cancel out the centimeter cube there, right? And what are we left with? So now we're left with kilogram per meter cube. So what I want somebody to put this in the calculator now. So you're gonna multiply across 13.6 by 1 million, and then you're going to divide that answer by 1,000 and tell me what the answer is. Who for something?
What? 13,600.
Right. Right. So you saw how I got it now?
Yes, sir.
Somebody's talking here. Alright, good. So that's how we got the 13,600. Alright. So now everything is lining up. So what would be the answer for the volume? What would be the answer for the volume?
times 10 to the negative.
Alright, so you said 2.39 times 10 to the
Times 10 to the negative 5.
negative 5. And the unit there is meter cube. Correct?
Yes, sir.
Alright. And if we had done it with the regular units, right? So if we had done it using the regular units, it would be, oh, we already transposed there. If we had done it with the regular units, it would be 325 divided by 13.6 grams per centimeter cube, grams there. So the volume here would be equal to 23.9 centimeter cube. Alright, so that's what you would get if you worked it without conversion. So it's best to do the conversion and have it in SI units, and you're sure of your marks than lose marks for not converting. Alright, is that clear?
Yes, sir.
Alright, next question to get our 15 marks. Calculate the relative density of gasoline using the density of mercury as the base quantity for comparison. Alright, so we're calculating what here?
Relative density.
So we're calculating relative density, right? And relative density is found by doing what?
The mass divided by the volume.
No, that is for normal density. We're talking about relative.
Density of the substance.
So the density of the substance, yes. Density of substance in question divided by
Mass.
the density, no mass, density
No, that's the
of the reference. The reference substance or the base substance. So this is the general formula for relative density. Anytime you see some relative, it's actually comparing one thing to the next, right? So I can say that I am comparing my speed relative to the speed of the earth. That is my relative speed, right? So nothing is really absolute here. So with relative density, we are trying to compare the density of the substance in question with the density of the reference substance. Now the question says we should use what as the base or reference substance?
Density.
Alright, so we should use density of mercury as the base quantity. So what is the density of mercury according to the question?
It would be 36 centimeters.
Alright, so we're using the kilogram per meter cube or we're using the grams per centimeter cube? Which one?
Can we
So
use
anyone
per centimeter.
Alright. So we can use any pair, but we have to choose the pair we're using. So I'm gonna be using so this is relative density equal reference substance 13,600 kilogram per meter cube. And what are we comparing it to now? We're comparing it to
The density of gasoline.
Density of the gasoline.
right. So the density of the gasoline that we found was in kilograms per meter cube.
8 kilogram
680, right?
per meters cube.
Alright, so 680 kilogram per meter cube. So when we divide that, you notice that the units are going to do what?
Cancel out.
They're gonna cancel out.
Portionless.
Alright. And that means is there a unit for relative density?
No, it doesn't.
Alright.
Dimension.
So this is one quantity in physics that there is no unit for. So when we write the answer, we don't need to put any units. So what's the answer?
0.05.
0.05.
So you get 0.05. No units. Alright, we all good with that?
Yes, sir.
Yes.
Alright. So please remember that there is a difference between density and relative density. With the density, you're actually trying to find the actual density of the substance or solid or whatever that thing is. You're trying with the normal density, you use mass over volume to find the density of that specific object or substance. With relative density, you are comparing one density with another density, which is the substance that is in question, that is the gasoline, and you're comparing it to a base or reference substance. Now normally we use water as the reference substance, but because the question says that we should use density of mercury as the base substance, we use density of mercury. Alright?
Yes, sir.
Alright, moving on. So that was basic stuff. Which topic should I go into next? I'm gonna go into, should I go into moments or pressure?
Repeat what you said a while ago. Moments.
Sir,
Moments.
I beg you.
What do you want me to repeat?
You said about the relative density.
Alright, and the normal density formula?
Yes, sir.
So the normal density formula helps us to find the density of a specific substance or object. That's what normal density quantity does. The relative density, it compares one density to another. So it compares one substance density to a reference density. That's the difference. And the relative density has no units because when you divide two same quantities, they cancel out.
Okay, sir. Thank you.
Alright. Alright, what was the topic? Moments or pressure?
Moments, sir.
Moments.
Then pressure.
Alright, moments then pressure. Alright, so this is recent paper 2021. And it asks you to define what a moment is. So tell me.
Turning effect of a force.
Go again.
The turning effect of a force.
The turning effect of a force.
Sir, can I?
That sounds like a two or a 1 mark. Be more specific.
Sir,
Mhm.
is it when the clockwise turn is equal to the anti-clockwise turn on a pivot?
No, that is the conditions. That is
Sir,
condition.
Oh, the perpendicular distance from fulcrum?
Alright.
Sir, the moment of a force is the turning effect about a given point,
Alright.
and it's calculated using the product of the perpendicular distance and the force.
Alright. Sound like you could get the 3 marks. So here's the trick to remember in this. All you have to remember is the formula. So the formula for moment says that we take T is equal, which stands for moments, is equal to the force times perpendicular distance. And the 90-degree sign there just represents perpendicular distance. So if you remember this formula, you remember the definition. So what we're going to write here is that the moment of a force is the, and since these two things are multiplying each other, we're going to say it is the product of the force and its perpendicular distance. And where is this distance taken from?
From the fulcrum.
From fulcrum. What's another name for the fulcrum?
The pivot.
The pivot. Alright, so of its perpendicular distance from the pivot, right? Or you could say from its from the point and line of action. Can use that as well. So these three elements are important, saying that it is the product of force and its perpendicular distance, and you must mention that it's from the pivot, right? And you could have stated that, but we leave it at that. Alright, so that's 3 marks. Next question says center of gravity. How we find the center of gravity? How we define. Sorry.
Gravity is the point on a body
Mm-hmm.
where all the total
Alright, so
where all the weight is equal.
okay. The last part not so clear. Anybody else wanna try?
The point through which all the weight of a body is acting.
Alright, the point through which all the weight of a body acts. Yes, that could go. Anybody else has a different variation?
The point through which the total weight of the body is considered to act.
Okay, the point through which the total weight of the body is considered to act. Alright, all those sound correct to me. So which one are we gonna use? So let's use center of gravity of a body is the point through which which one of them are we gonna use? Total force, all its weight.
Total weight.
Alright. To which its total weight seems to act. Alright. Alright, 2 marks.
Sir,
Mm-hmm.
could you say that it's a point of body where all weight is focused as well, or no?
All weight is focused.
Yeah.
All the body's weight.
Yeah, like a point of a body where all weight is focused.
The last part seemed kind of off, but you'd probably get a 1 mark for that.
Oh, okay.
But the best thing to do is to stick to the definition that is given in your concise or textbook. Alright, so you're sure of the mark. Alright. Next question. State 2 conditions necessary for a body to be in equilibrium.
The total
Okay, one at a time. So we're going to use raise of hands now because I realize that many persons are answering.
The sum of the clockwise moment should be equal to the sum of the anti-clockwise.
Alright, that's one. And use the reason feature next time, Jade.
The total upward force must be equal to the total downward force.
Does it have to be upward or downward?
No, sir.
No, it doesn't have to be to upward or downward. So let's correct that. So number one, the sum of the forces in any direction is equal to the sum of forces in the opposite direction. Alright, and the reason why we use this general term here, any direction and opposite direction, is because your forces, yes, they can be acting upward, right, and downward. Yes, that's a possibility, right? But also there's a possibility that the forces can be acting diagonally, right? And it still can be equal but opposite. Do you see that?
Yes, sir.
Alright, so we don't say that this is the sum of the upward and downward forces, because that's being too specific with the condition. So we say instead that is the sum of the forces in any direction. It must be equal to the sum of the forces in the opposite direction. That covers everything. Alright, number two now. Second condition says that the sum of the what now?
Anti-clockwise.
Sum of the anti-clockwise. Clockwise what? Moment, yes.
Movement.
Sum of the anti-clockwise moment is
Equal to the clockwise.
equal
What paper
to,
is this?
this is 2021, question 2.
Alright, so copies.
The sum of the anti-clockwise moment is equal to the sum of clockwise moments. Right? Full stop. Alright, we get that?
Yes, sir.
Alright. And I'm gonna tell you the summarized version of the two. So for number one, you could also say that the resultant force in any direction is equal to 0. You could say that for number one as well. And for the summarized version of number two, you could say that the sum of the moments about any point is equal to 0. Alright, so those are the summarized versions. But it's best to know these versions because they help you to remember the equations. Alright? Are we clear?
Yes, sir.
Alright, so here we are going to apply all this knowledge now to a situation. Right? So it says figure 2 shows below a diagram of a non-uniform wooden plank. That's very critical. AB, which is 2.0 meters long and it weighs 1,000 newtons. The plank is supported from a ceiling by 2 vertical springs P and Q. The plank is attached at the distance of 0.5 meters from each end. C is the center of gravity as shown in figure 2. Now, when the plank is horizontal, the tension in the spring is 600 newtons. And we have to calculate the tension in spring Q. So the best thing to do before you do anything is to identify your forces on the diagram. Right? So where would I put my forces if I was supposed to label this diagram? The ones that are not there.
Sir, may I attempt?
Yes.
wouldn't it be a downward force?
Where would that go?
It would be beneath Q and P.
Q and P. So what would keep the uniform wooden block up? If everything is going down.
Up.
Yes, if everything is going down.
Repeat the question.
So we are trying to identify the other forces, right? So we have the weight here, that is one force. But we're trying to identify the other forces that are in this diagram.
Yes, sir.
And the question says that the beam is hanging. It's hanging. Yes, so Jade, go ahead.
The tension in the spring.
Alright, so the tension in the spring, which direction is the tension going? Up or down?
Up.
Alright. So to counter the weight that is pulling the beam down, there is a tension in the spring. Right? There is a tension in the spring. And there is a tension in the spring at Q. Do we all see that?
Yes, sir.
Alright. So it says in the question that P is 600 newtons. So we know what P is. So P is 600 newtons, right? And we don't know what Q is, but we know what W is. W is 1000 newtons. So here it says that we are supposed to calculate the tension in spring Q. So given all the information here, which one of these conditions would be suited to help us calculate this?
Use your mic, Alvin. Sorry about that, sir. Continue.
Alright. Thank you for that. So given the information here, which one of these principles or condition would help me to find the unknown Q? Jade.
So the sum of the
forces
upward force.
Alright, so is that number 1 or number 2?
Number 2, sir. I changed my answer.
Number 2? Why would you use number 2?
I was saying number 1 first, and I heard someone else say 2, so.
So you need to stick to your thinking and your rationale, right? So if you look at the diagram, we know we have 3 different forces. We know 2 out of the 3 forces, and we have 1 force remaining, which means that we are able to find the unknown force using the first condition, right? So there's no need to use the moments one because you already have more than enough forces. If you had 2 unknown forces, then you would need to resort to the other one, right? But you have all the forces, you only need to find one. So we're going to use condition 1, which says that the sum, in this case now, we can specify that these forces are going upward and downward. Is that clear?
Yes, sir.
So in this situation, we can now specify in our equation that these forces, some of the upward forces is equal to the sum, right? This symbol here is just representing sum of downward forces, right? So now we need to put all the upward forces on one side, all the downward forces on one side. So name the forces that are going upward. Name them. What's the symbol representing them?
P and Q.
So we have P and Q going upward. So P, and it says sum, so P plus Q is equal to the downward now, which is W. Alright, so that's how you want to set it out. Now we're going to just substitute in the information. So P is 600 newtons plus Q, that's what we're trying to find, equal the weight, which is 1000. Right, 1000 newtons. So that means Q is equal to what?
1000 minus 600.
Alright, very good. So we are going to subtract 600 from both sides. Right, so we subtract 600 from both sides. And so our answer is going to be equal to 400 newtons. So capital N. Everybody clear?
Yes, sir.
Yes, sir. Yes, sir.
Alright. So the person who is J in the chat, again, the paper is 2021. Alright, moving on. He says now, by taking moments about A, determining the horizontal distance from P to C. So we are to take the moments at A. So the A is right here. So we're going to be taking the moments at A. And we are to determine the distance. So let me put that in a different color. The distance P to Q. Sorry, P to C. So we are to determine this distance here. Alright, I'm going to call it D. So with this information now, which one of these conditions will we use to find our answer? So we'll use 2, correct. Okay, there's somebody in the chat saying that they don't understand. What exactly don't you understand? Is it this question or is it the new question? Okay, the first one. Okay. So for the first one, right, if we look at the question, it gives us some information, right? So we have tensional forces in the springs, which are the upward forces, and we have the weight, which is the downward force. The question already told us that P is 600 newtons, right? And the weight is 1000 newtons. Which means in order for us to find the answer, we have to use the first condition that we identify here, which involves only the forces. So because we have all the other forces except one, it gives us the autonomy to use the first condition, which only focuses on the forces. So I hope that was clear to that person. Alright, moving on. So by taking moments about A, we must determine the horizontal distance P to C. Right? So I heard you said that we should use condition 2, that's correct. And what's the reason for us using condition 2 with moments?
Is it because when we're talking about clockwise and anti-clockwise movements in this instance?
Yes, so there is it says we must take moments by A, so and it involves a force and a distance. So forces and distance are involved in this question, so we have to use the moments part. So there's a question in the chat. Sir, in all cases with tension be an upward force, it depends on what is pulling it, but the tensional force always opposes the force that is, it always goes against another force. The tensional force always goes against another force. So in this case, because the weight is going down, right, and the spring is pulling up the beam, then the tensional force is going to go opposite to the other force. Alright? So if we look at 2 persons pulling on a rope for tug of war, right, then the tensional forces would not be going up and down because you have 2 persons pulling on the rope, right? So if you have 1 person pulling on the rope, so here's the rope, and there's another person over here, right, pulling on the rope as well. So one person is not applying a force one way, another person is applying a force another way. The tensional force would be different in this case, right? Because one would oppose the other. So it's not necessary that all situations will have tensional forces going up, right? It depends on the situation. All right. by taking moments at A. So we must determine the distance PC. So we're going to write out our formula, or worded equation. So the sum of the anticlockwise moment is equal to the sum of the clockwise moments. Alright, so the fact that we're using this, we need to identify our clockwise and anticlockwise moments on the diagram. So let me use another color. So we're identifying our clockwise and anticlockwise moment now, and remember we're taking it from the pivot at A. So all moments are going to be taken from each force, and we're going to use the pivot to determine if it's going to be clockwise or anticlockwise. So let's focus on the moment that is at P. So will this force, this tensional force at P, will it cause a clockwise or an anticlockwise moment?
Clockwise.
Clockwise. Alright, so I always tell students to use their pencil to help them with this. So you're gonna set your pencil horizontally with the beam. So set the pencil in the position that the beam is, and then you're gonna apply a force upward while keeping one end of the pencil fixed and applying the force on the same side as in the diagram, and tell me if you get a clockwise or anticlockwise moment.
Oh, you get anti-clockwise.
Alright, so you see how helpful the pencil is? So when you turn the pencil from the, let's say you're using the right side, when you turn it, when you push it upward, it's gonna cause everything to rotate that way. Do we agree with that?
Pencil's going right.
Do we agree with that?
No, sir.
Why not?
My pencil's going right.
It's going right.
Yeah,
Are you applying the force upward while keeping
Yes,
one
sir.
end fixed?
yes, sir. I'm applying it from the left, and I'm pushing it up.
No, but you need to apply it from the right. This is on the right of the pivot. The force is on the right of the pivot.
Oh, okay.
Right. So this moment here for P, right, and the distance from P to the pivot will give us an anti-clockwise moment. Right? So if that follows for P, what about Q?
Clockwise. Clockwise.
Again, use your pencil first. Use your pencil. So set your pencil in the position of the beam. Put your finger at one end that is fixed to represent the pivot, and then apply the force upward. And tell me what's the moment there? Is it clockwise or anti-clockwise?
Clockwise.
You get a clockwise moment when you push it up.
Anti-clockwise.
Alright.
Anti-clockwise?
It's anti-clockwise. I don't understand how persons are getting clockwise. Alright, let me see if I can use something here to help you out.
Sir, I think we were getting anti-clockwise because we were assuming that, because the formula says both, we were assuming that we needed to have both to plug in.
Right. So watch this now. Alright, so let's see if this will work. Alright, so this is my ruler, right? We're seeing the ruler. And my ruler is representing the pencil that I asked you to use. So my ruler is in the position of the beam. Do we see that?
Yes, sir.
Now, if I apply a force upward on the right side of the ruler, that is happening at Q here, if I apply a force upward while one end is fixed, what is happening? What moment is this causing?
Anti-clockwise.
Isn't that anti-clockwise? So let me go back. So we're at horizontal. It says apply an upward force on the right. The pivot is on the left. So we apply our force this way. So this is anti-clockwise. So this has to be an anti-clockwise moment. Does that make sense?
Yes, sir.
Alright. So I'm bringing back this now down. Bringing back this level. What about the other force now? W.
Clockwise.
Alright, so we do the same thing. So now the force is going downward, causing a clockwise moment. Do we see that? Alright.
Yes, sir.
So now we can identify this one. So this force here is causing a clockwise moment. So this is clockwise. So once we have identified our anti-clockwise and our clockwise moment, then we can now do the question. Alright? This is pivotal to you getting the question correct. Now remember, for a moment, to calculate a moment, we need a force and what else?
Distance.
We need a force and a distance. So all the forces that I identify, all the distance must be taken from the pivot and they must be perpendicular. So for example, for my first anticlockwise moment, which is at P, I'm going to use P, the force for P, and I'm going to use the distance from P to the pivot. Alright? But first, I want to label these distances. So the force at P is 600 newtons. Do we agree with that?
Yes, sir.
Yes, sir.
And the distance from P to the pivot is how much?
0.5 meters.
0.5. And I'm going to call this D1. Right? Now, the next anticlockwise moment is at Q. So that we have the force at Q. We found that. Right? The force at Q was what?
400.
400 newtons, right? And we're gonna take the distance from Q, right? So the distance must be taken from Q, right? And we're gonna take that distance straight to the pivot. So that distance, I will call it D2. So that distance is bigger than the first distance, right? Because it's further away from the pivot, right? And then my final distance now is gonna come from my force that is going down, right? And the distance there from W to the pivot, what is that distance? One. How do you get one?
There, because 0.5 plus 0.5.
How do you know that D in green is 0.5?
There, because the pivot is at the end right there.
Yes.
And it kind of meet in the middle.
In
So
the middle?
it-
Who?
Sir,
Mhm.
it looks equal.
It looks equal.
Yes, sir.
Alright, but here's the key thing that the question pointed out to us. It said that the beam is non-uniform. Right? So if it is non-uniform, right. So if it's non-uniform, it means that the center of gravity does not mean that the center of gravity is in the middle. Right? For a uniform body, the center of gravity is in the middle. But for non-uniform bodies, the center of gravity can change depending on where the mass is. Most of the mass is. Alright, Nathan, you had a hand up?
Yes, sir. I was gonna answer the question. So, our I got 1.5 meters for the distance because it says the distance from A to P is 0.5
Mm-hmm.
and the whole plank is 2 meters, so you have to subtract the 0.5 from the 2.
All right. However, remember that this distance here from W to the pivot is not representing half. It's not representing half because it's not a uniform beam. It's a non-uniform beam. So we do not know the distance from C, which is the center of gravity, to A. We do not know it. We cannot find it out. We have to use the equation to help us there. So the distance from A to W is actually 0.5 plus D. That is the distance. It's not something that we can calculate right now. So that's what we'll be using. Is that clear?
Alright, so.
Alright. So let's now substitute in these values into the equation here. So we're gonna put in all our anticlockwise moments, and remember, for each moment you must have a force and a distance. So for our first anticlockwise moment, it's P times D1. So it's P times D1.
I have so much money and time on physics to not get at least a breakthrough. Which was a breakthrough?
Okay, Sharika. Alright, so we have P, which is the force, times the distance that we identified for that moment, plus we have Q times the distance from Q to the pivot, which is D2. So we have Q times distance D2. Alright. You understand that I just did?
Yes, sir.
Alright. Now, so we identify all our anti-clockwise moments, and now we're going to identify our clockwise moment. So for the clockwise moment, it is W. So it's W times the distance from W to the pivot. Now we don't know what that total distance is, so all we're going to do, we know that we have to add this plus this to get it. So we're going to put that in bracket. Alright, so it's going to be 0.5 plus D, right? That's going to give us the answer there. Alright, and remember, our objective is to find out the distance from P to C. Alright, so we want to know what the small distance is. So all we have to do now, right, we have one unknown, plug in the information that we have, and we will solve the problem. So for P, what was our force for P according to the diagram?
600.
600. Alright, so we have 600 newtons times, what's the distance from P to the pivot?
0.5.
So we have 0.5. Yes, very good. So 0.5 meters. Right, plus next moment. So Q, we calculated Q to be 400 newtons times the distance from Q to the pivot.
1.5.
1.5. Very good. So we took this out of the 2.2 because the entire beam is 2, and we know this distance, so the rest of it must be 1.5. So we have 1.5 meters here, right? Equal, what is equal to now? Is equal to W times 0.5 plus D.
Sir, we know W, right? Which is 1,000.
Oh yes, we do know W. Sorry about that. We do know W. So W is 1,000 newtons. Thanks for that. Alright, so it's just a matter of calculation now. So let's do the first bracket here. 600 times 0.5. What do we get?
300.
300. So that's 300 Newton meter, correct? Plus 400.
600.
400 times 1.5 give us 600.
Yes, sir.
600 Newton meter. I remember the units equal. How do we do this now? 1000 times bracket 0.5 plus D.
We're going to work on the bracket first.
Excuse me, sir.
Mm-hmm.
Sorry, I'm just coming back in again. How do you get the 1.5 meter for distance 2?
Okay, so distance 2 is the distance from Q to the pivot, right? But we know what the distance from the other side is, which is 0.5. And we also know the entire length of the beam, which is 2. So what we did was to subtract 0.5 from the 2 to get the remaining distance, which is D2.
Okay, sir.
Yes. Jade, you had a hand up.
Why are you multiplying the 0.5 times D instead of adding?
I'm adding it. I'm not multiplying it.
Oh, sorry. I was looking at the wrong thing.
Okay. So we're adding 0.5 to D. Is it possible for us to solve this, the bracket?
No, sir.
Okay. So what do we need to do with the 1000 to get rid of the brackets?
Multiply. Right.
Alright. So what we're going to do is multiply out the bracket to get rid of it. So we're going to multiply 1000 times a half and 1000 times D. So 1000 times 0.5 is what?
500.
So that's 500 Newton meter plus 1000 D, right? That's what we're trying to find. Alright, does it look easier now to solve?
Yes, sir.
Yes,
Alright.
sir.
What are we gonna do now to get to D? D that we want.
Add the 300 and the 600.
Alright, so let's do that first. So 300 plus 600 give us
900.
900. So that's 900, not 9000, 900 Newton meter equals to 500 Newton meter plus 1000 D. Next, what's next?
Yeah, bring over the 500.
Bring over the 500 by doing what?
Subtract.
Alright. So I'm going to subtract 500 on both sides. So 500 newtons on both sides. Newton meter. So this is gone. So that's not, or 0. So let's leave us with what now?
400 Newton meters.
400 Newton meters equal 1000 D. Alright, what's next?
Divide 1000 D by 400 Newton meters.
Alright, so I remember that the 100 is in newtons, right? See that right there? I should have brought it back here, but I don't want to confuse you with that. So remember the what is 1000 newtons, and dividing this side by 1000 newtons. So what's the answer for D? So this cancels out that. And so the answer for D is equal to 0.4 meters. Do you get that?
Yes, sir.
Alright, so that means the total distance, right, from C to the pivot would be 0.4 plus 0.5, which would be 0.9. That's the total distance. But what the question asked us to find was only the distance between P and C. And we did that by using the second condition of equilibrium. Alright, everybody follow that?
Yes, sir.
Alright, so if a moment's question come tomorrow, you should be able to do it. Alright?
Yes, sir.
Alright, another thing to note about the moments question. You see, if you are given two unknown forces in the question and you don't know them, what you can do to make your life easier is to make one of those unknown forces, put the pivot there. So you put the pivot directly under it. Why would I want to do that?
Because it would mean that that's where the weight of the force acting, or the downward force is acting.
What would that mean in terms of the moment of that at that point? If I should remove the pivot from A and I should put it where the P is, right? What would happen to the moment at this point? Alright, nice, Brit. Very good. So Brit have the answer. It would be 0, right? Because there is no distance that is at P. So whatever force is at P that is unknown, if we multiply by the distance which is 0, it is out of the equation and it makes our job easier. Is that clear? Hello?
No, sir. One more time, please.
Alright, so let me go back. So let's say, remember this question asks us to put the pivot at A. But in this question, we knew all the forces, right? There was only one unknown force, which was Q. So there is no problem with finding the answer for this question. But I'm saying to you that if you get two unknown forces, you can remove the pivot and put it where one of those unknown forces are, and that automatically eliminates it from the equation, so you can find the other unknown.
Alright, sir.
Alright, so just bear that in mind. But otherwise from that, wherever they ask you to put the pivot, you put it there. So in this question, it says it should be at A. Alright, so that is the end of that question. Oh, it's not finished. So it says here, state why the center of gravity is located closer to P than to Q. So look at the values we got for P and Q. So Q was equal to 400 newtons. Why is it that the center of gravity is closer to P than to Q? Yes, because
of the weight.
Because of the weight, because it's larger. Jade, go ahead.
I was gonna say maybe it's because there's more tension on P.
Alright. So that's that one thing. So there is more tension on P, and also because the beam is non-uniform. Right? So the center of gravity is not going to be in the middle. It's gonna be closer to whichever force it needs to go closer to in order for it to be in equilibrium. So if you think about it like a meter rule that is non-uniform, in order to balance it, right, you have to move the center of gravity has to be closer to the heavier side so that the other side can balance off. Alright? So the reason here is because one, the beam is non-uniform and the larger tension is on the left. Alright, so you can write this is a one mark question. Simple reasoning. Alright, so we're done with moments. Let's go to pressure. Are you ready for pressure?
Yes.
After pressure, you can do electricity and magnetism.
I was saving that for last still.
Alright, no problem.
Alright. So page 1, pressure. Alright, so this question, 2022 paper, define the term pressure, state the SI unit. Easy 3 marks question. Define the term pressure.
Pressure is the force acting normally per unit area.
Alright, very good. So if you remember the formula again, P is equal to force over area, and this is pressure outside of a liquid. So if you remember the formula, you know the definition. So pressure is the force acting You said normally?
Yes, sir.
Normally per unit area. All right. So that's one part of it. What about SI unit?
PA, let's say Pascal.
So it's Pascal
Pascal, sir.
or what?
Newton meter.
All right. So if what's the SI unit for the force? Newton. SI unit for area?
M square.
Meter squared. So that means SI unit is Newton per meter square, or we represent this as Pascal. Right? So Newton per meter square is now named after Pascal because of his contributions to physics. Alright? In that area. Alright. Next question. Calculate the liquid pressure that a diver experiences at a depth of 0.5 kilometers below the surface of the sea. Let me zoom in on this. Given that the acceleration due to gravity, G, is 10 Newton per kilogram and the density of seawater is 1025 kilogram per meter cube. So first thing, what do we need to do?
Write the equation.
Write the equation. Right, we can do that, but let's identify what we're given. So what are we given in this question?
The gravity, the depth, the height.
We're given G. So we're given G. We're given the depth, which is change in height. Right, so that's 0.5 kilometers. And we're given the density of seawater, which is 1025 kilogram per meter cube. Alright, and Britt has put in the correct equation. So now that we know this is all that we know. And what we're trying to find here is the liquid pressure. So what we're trying to find is the change in P. That's the unknown. So this is the given, this is the unknown. Alright, so now we select the formula. So the formula here for pressure in liquids, everybody can see it. Change in P is equal to
68 times gravity times height.
Times change in height. Alright, they don't always give you the change in height, you know. In this question, they give you the change in height. But if you were not given the change in height and you were given two heights, so for example, they say that you move from 10 meters to 12 meters. What's the change in height here?
2.
It would be 2 meters. Very good. So you have to look out for that in the question. If they don't give you the two heights for you to calculate the change in height, then you just use what they give you as the change in height. So the change in pressure is going to be equal to the density of the seawater, which is that, times G, which is 10 Newton per kilogram, times the change in height. Now, should we use but the 0.5 kilogram? Kilometer.
You can convert it.
Should we use it or should we convert it?
We should use it.
Alright, give me the reason why you shouldn't use it.
Sir, forgive my background, but because we have to convert it. Remember that pressure is meters squared and that's kilometers, so we have to convert from kilometers to meters.
Alright, very good. And also, if you notice, if you look in the density, you will see that the unit that represents the length or distance or depth is in meters as well. So we want to ensure that all our quantities are in similar units. So if this is in meter cube, that means the depth over here has to be in meters, right? You cannot have conflicting quantities. So we use similar quantities. So just like in the gravity, acceleration due to gravity is in Newton per kilogram, and in the density you're seeing kilogram here, that is good. But because there is no meter here, we need to convert the kilogram to meter. So how do we do that? Alright, so 0.5 kilometers to meters. What are we moving from? Are we going from small to large or large to small?
Large to small.
So a large unit to a small unit, we should do what? What operation? Multiply. And how much are we multiplying by?
1,000 or 10 to the power.
Alright, so we're multiplying by 1,000. So it's 0.5 times 1,000, which would mean that our answer is
500.
So 500 what? Dumplings?
Meters squared.
Where you get square from?
Oh, cube, my bad.
Cube? We're dealing with depth. So it's meters. Alright, so remember, a meter square represents area, meter cube represents volume, and just meter represents one dimension, which is either length, depth, width, any of those one dimensions. Alright, I'll give you a pass for that one. So the change in pressure is equal to, what's the answer here?
Sir, I get 5,025,000 pascals.
5,025,000. 112 or 125?
125,000 pascals.
It's pascals. Right, I'm gonna write it in the units I get from the calculation first. So kilogram cancels out kilogram here. Do you agree with that?
Yes, sir.
Yes, sir.
Alright, this meter cancels out one of the meters here, leave us with 2. Agree with that?
Yes, sir.
And so our unit is Newton per meter square or Pascal. But we want to represent this number, this large number, in scientific notation. How do we do that?
Sir, would it be 5.125 times 10 to the power of 3?
So 5.125 times 10. How much jumps?
Oh, you know, the 10 to the power 6.
Alright, so the power 6. And put back our pascals. Alright, so if we're asked to convert our answers into scientific notation or standard form, that's how you do it. These things come up in the paper one, so you must know how to do
Wouldn't
it.
it be to the power of negative?
Cannot be negative. If it's negative, then that means I have to move the point to the left. And we want to get back to this. So when you convert this down here, we must get back to this. If I put negative here, I have to move the point this way, which is not going to give me back this. You follow?
Will I have to put the answer in standard form?
It is advised. It's a rule of thumb, but it's not a must. Cool?
Yes, sir.
So as Reed said in the chat, negative power means that you get a small number. So if the power is negative, we go get a small number. But our number here is very large. Alright? Alright. Moving on. Oh, that's the last one.
Sir, are we going to do Newton's last night?
Yes. Why not? Alright, we're still under pressure. And the weight and those stuff. 2012. Question 3. So we're looking at a yacht. Alright, so the yacht shows figure 1 has a mass of 8,300 kilograms. And we're asked to determine its weight in air, given that the acceleration due to gravity is 10. So we're given the mass, which is 8,300 kilograms. Right? We're given G. What will we use to find the weight?
Multiply mass by
M times 3.
Alright, very good. So it's M times G. Somebody said in the chat, if what I give you now may come on the exam. Yes, it's a strong possibility. They can ask the questions from any topic. Alright. Alright, so we have W equal the mass, which is 8,300 kilogram times G, which is 10 Newton per kilogram. So the answer for the weight is
83,000.
Daniela, the year for this is 2012.
Newtons.
So it's 83,000. What's the answer
Yes,
here?
sir.
What's the unit?
Newton.
Newtons. And if you don't know what the unit is, just cancel out what is in the equation. You have to find it out. Alright, next question now. Requires some reasoning. So it says for land transport, the yacht is secured on a trailer. Each tire on the trailer can support up to a maximum of 700 newtons. Sorry, 7,000. So each tire on the trailer can support 7,000 newtons. What is the least number of tires the trailer should have to support the yacht adequately? How do we work this out?
Sir, would it be that you divide the 83,000 by 7,000?
Brilliant. Brilliant. So let's explain this. So the yacht, right? So it says that we have 83,000. So the yacht is measuring 83,000 newtons in total, correct? One of the tires can support a maximum of 7,000. That's just one tire, newtons. So how many tires do we need to support the yacht? It's a very simple calculation. So the number of tires is going to be equal to the total what?
The total weight or the
Total weight divided by
the amount of tires.
Divided by the number that is supported by one tire.
Okay, so number supported
So
by
the
one
weight of one. So the weight of one tire, right? So it's gonna be equal to the total weight of the yacht, which is 83,000 newtons, right? Divided by the weight that can be supported by one tire, and we will know how many, the least number of tires that we need. So when we divide that, what do we get?
11.86.
11.86.
86. That's right.
86.
11.86. And the units cancel out here, so that means we're talking about a number. So do we go to the trailer company and say we need a trailer that has 11.68 tires?
No.
So what should we do?
11.
11? Really?
Well,
So what to
please.
the other 0.8?
8 can be rounded up.
Alright, so we go round up this number, right, to a whole number because we're talking about tires. So it's gonna
But
be,
it said least, sir. Least.
yeah, least. But you're not going to put 11 tires on the trailer. That's not gonna be, it's not gonna work. Right? So you still would need 0.86 more to support the entire weight. So instead of getting a half a tire or that you just round up the number. And if we go back to the diagram, let's see if they have it right here. How many tires are at the front of the trailer? Right here. How many tires are right here?
One.
Two.
Has to be two, right? One on this side, one on the opposite side, correct? Do you agree?
Yes, sir.
So two here.
Yes.
How many are here?
4.
So four. And how many are here?
6.
So 6 plus 4 plus 2 is what?
12.
Alright, so the least amount of tires. So we can get a trailer with more tires, which would actually support the yacht, but the least amount you need to carry the yacht is 12. That's what the question is saying. Alright, so you need 12 tires, alright? Does that make sense?
Yes, sir.
Alright.
Yes, sir.
Alright, next question. Many forces are acting on the yacht, yet it is still in equilibrium. So notice what it says. Many forces are acting on the yacht, yet it's still in equilibrium. State two conditions that must be satisfied for an object to be in equilibrium.
Those are the force acting on the object must be equal to the force of the object.
Alright,
So
Jade?
I said all thousand force is equal to 0.
Yes, that's one. Jade?
And the
Hold on. Sorry, there's two Jades. So it's Jade Physics now, not Jade Scott.
I was going to say that the sum of forces in any one direction should be equal to the sum of forces in the opposite direction.
Brilliant. So the next, and you can use the other person that went before that spoke about the resultant forces being 0. That's also 1. What's the next one?
Sum of anti-clockwise forces should be equal to the sum of clockwise forces.
Alright, what was wrong about our statement there? Please correct her, somebody.
Moments.
So it's not moments, it's not force, it's not anti-clockwise forces, it is anti-clockwise moments. Remember that. Alright, so very good read. So it's just a repeat of what we did a while ago, so I don't need to write it out again. Next, it says state the effect of the position of the center of gravity of an object. So state the effect of the position of the center of gravity of an object has on its stability.
So that all weight can act upon it?
So that?
All weight can act on it?
So we're looking at the effect of the position of the center of gravity and how it affects stability.
Because all the weight is acting at a specific point, the object becomes balanced?
Okay, not
Sir,
exactly.
A higher center of gravity decreases stability, and the lower center of gravity makes it more stable.
Very good, brilliant. So remember, when you looked at stability, there were certain factors that you learned that affect the stability of an object. The center of gravity is one of them. Can anybody else tell me the other two? So just to recap this for everybody.
Surface area.
Not the surface area.
Repeat the question, sir.
So there are 3 things that affect the stability of an object. So 3 things are 3 factors that affect the stability of an object. Number 1 is the center of gravity. Right?
Would it the forces that the turning forces or something like that?
No, that's for equilibrium. That's why when you want equilibrium, we're talking about stability here. Stability of the object.
Sir, would it be the base?
What about the base?
It's width.
Yes. Very good read. So it is the width or the size of the base, right? And number 3, what's the other factor that affects the stability?
Height.
The height. Not the height. Well, that would come under the height of the center of gravity. That's coming number 1.
The position of the line of action.
Position of the line of action, no. That would come under center of gravity. There's one more thing that affects the stability of the object.
The weight of the object.
The weight.
The surface area.
Not surface area, the weight. Alright, so you have to remember these. The weight also affects the stability of the object. So I'm going to get back to these two. Let me just give you a small scenario. So imagine we have a flat surface, and on that flat surface, let's create a cone. Right? And let's turn the cone upside down. So we're talking about stability here. Turn the cone upside down. Now, where would the center of gravity be for cone A? And where would the center of gravity be for cone B? Would the center of gravity for cone A be closer to the base, to the floor, or higher?
Floor.
So it's closer, right? So the center of gravity for A would be closer to the ground, right? Because the most of the weight is down here. Do we see that?
Yes, sir.
So the center of gravity would be there. So center of gravity is where all the weight seems to act, right? Now, for B, where would the center of gravity be? Higher or lower?
Higher.
Alright, so the center of gravity would be higher, right? Let's get this straight. So the center of gravity acts through the center there. Alright, so celebrate. Alright, so with the center of gravity being lower, how does this affect the stability of the object? Somebody said it earlier.
It increases the stability.
Alright.
Makes it more stable.
Alright, when the center of gravity is higher, what happens?
The object is a bit unstable.
It's a bit unstable, it is less stable, right? So, to answer this question, right, we would say that the lower the center of gravity, the lower the center of gravity, the what?
The more stable the object is.
The more stability, or more you can say that as well. So I'm putting stability for a short. Alright, so that's how the center of gravity affects the stability of an object, which is why you will see that race cars, they are designed to be closer to the ground, right? And most of their weight is closer to the ground, right? For the width now, how does the width affect the stability of the object? Looking at the two scenarios.
So, the wider the width, the more distribution of the forces of the object, or the more distribution of the weight of the object.
I wanted to tell me about the stability. How does it affect the stability? Is it more stable or less stable?
The wider the width, more stable.
Alright, who was going a while ago? Bianca? I haven't heard Bianca. Go ahead, Bianca.
So I was saying the wider the width is more stable the object is.
Very good. So the wider the base, the more stable the object is. The narrower the base, the less stable it is. Right? So they can ask you that as well. What about the weight? How does the weight affect
object becomes.
All right, very good. So a larger body is harder to topple than a body that has a light that is lighter. So the heavier the body, the harder for it to be toppled. So think about it like a person that is fat with a person that is slim. The person that is fat, if you try to move them or to topple them over, it takes more force to do that. While a person that is slim and has a little weight, it is very easy to topple them over. So that's how weight affects the stability of the object. The heavier the object is, the more stable it will be. Everybody understand that?
Yes, sir.
Yes, sir.
Alright.
Yes, sir.
So these what we refer to as factors that affect stability. Up here, we look at the conditions, which we did earlier in the other paper. The conditions. So the first condition speaks to the forces. Sum of forces acting in any direction is equal to the sum of the forces in the opposite direction. And the second condition speaks to the moments. So the sum of the clockwise moments is equal to the sum of the anti-clockwise moment. So once you see these two terms in the question, conditions and equilibrium, we're talking about those two. Once it mentions factors that affect stability, we are looking at these three. Everybody's clear?
Yes, sir.
Alright. State Archimedes' principle.
When an object is wholly or partially immersed in a fluid, it experiences an upthrust which is equal to the weight. It is equal to the weight of the water, weight of the fluid displaced.
You just read that or you just recite that?
I recited it.
Very good. Very good. Alright. So, Archimedes' principle states that. So, it. Alright. Nice, Daniela. I hope that you type that from memory. So, it states that a body that is completely or partially immersed in a fluid what happens?
It
experiences an upthrust, or what's another name for upthrust force? Starts with a B.
Force.
Buoyance or buoyancy? Which one? Buoyancy. So you can say buoyant force or you can say buoyancy force. It's talking about the same thing. Alright, so experiences are upthrust that is what? That is equal. So let me put that in red. That is equal. So the upthrust is equal to the weight of the
fluid displaced.
Alright. So the weight. What am I doing here? So the weight.
Good day.
Good day.
I already have the subject, but it's interesting to be in the class,
Okay, welcome, sir. Brings back memories?
Trinidad.
Weight of the fluid displaced. So that's the 2 marks. So you must mention that the body can be completely or partially immersed, and you must mention that it will experience an upthrust that is equal to the weight of the water displaced. So whatever amount of water that object displaces in the water, the weight of that particular amount of water is equal to the upthrust force, and that is why the object will float, right? So for example, if I have this box, right? And it's in the water here. This box here will have a force going downward. What's that force? What's the name of that force?
Gravity.
No. This force is related to the mass of the body. Start with a W.
Weight.
The weight. Very good. So remember, if there's a mass, that means there must be some force acting on it, right? Causing it to go down, which is the weight. And then now we have the water that is exerting a force against this, which we refer to as the upward force or
Upward thrust.
the upward thrust, buoyant force. So the buoyant force, right? So what Archimedes discovered is that whatever amount of space this part of the object is taking up in the water. So let me just represent it over here. So let's say, so this is the amount of water that part is taking up, right? What Archimedes discovered is that this amount of space that part of the object takes up, it is equal to the upward or up thrust, right? You discovered that when these two things are equal, then the object has to float, right? So when the displaced weight of water is equal to the up thrust, then the body will float. So when U is equal to W, the body will float, right? But what if U is less than W? What will happen to the body?
It will sink.
All right, so the body will sink, and that's because the weight is greater, right? So it will cause everything to go down. So the genius behind the boats that are created, the massive boats, is that they have found a way to ensure that whatever amount of water that is displaced by the boat will be equal to the up thrust force, which keeps it afloat. All right. So as we move on to the next question, it says that the yacht's hull is made of steel with a density of 7,850 kilograms per meter cube. That's the density of steel that makes the yacht. Explain how the yacht is able to float in the seawater of density which is less, 1,025 kilograms per meter cube. How do we explain this?
Can I ask the hull first?
The hull, that's,
Yes,
I believe the hull is this section of the ship, this section of the yacht.
Alright.
Right. So we want to find out, since the density of steel is higher, of the hull is higher than the density of water, how is it possible for the yacht to be floating when the density is higher than water?
Victor, can I answer?
Yes, Jade. Scott.
I would say based on how it's shaped and the center of gravity.
Based on its shape and the center of gravity, I need you to connect it back to Archimedes' principle.
Okay, so Archimedes' principle says that when an object is fully or partially submerged is equal to the weight. It makes an up thrust that's equal to the weight of the fluid. So I'm guessing that the base of the air, it creates like an up thrust strong enough to be equal to the displacement of the water.
All right. Anybody else? Anybody else? All right. So Jade, I want you to look at it now in terms of the overall densities. So this was giving you the specific density of steel and the specific density of the seawater. But now I want you to look at the overall densities. So when you compare the density of the hull of the yacht and compare it to the overall density of the seawater, what will happen there? Will it still be more or less?
Repeat what you said, sir?
So I wanted to compare the overall density. So this is just specific to steel only, but the boat is not made up of steel only. There are other materials that consist of the hull. So I wanted to compare all of that overall density with the overall density of the sea water itself.
So would it be that you subtract it?
No, you don't need to subtract it. I said just compare them.
Okay, so it's definitely larger. And you said that not all of it is made of steel.
Not all of it
So
is
I
made of steel.
actually don't know how to approach this question.
All right. Let's
Would
see.
the ship be hollow or something like that?
Yes, that has to do with that. So in the hollow space, so let's go along with that. The hollow space, what's contained there? What's in the hollow space? Air, right? Right. So the yacht, the hull of the yacht is designed so that it takes up a lot of space, and inside of that is air, right? And so because the hull is made up of other types of material, when we compare the overall densities of all those material with the overall density of seawater, right, then when we look at it from a bigger picture, we will realize that the overall density of the seawater would be less when we compare it to the overall density of the boat. Do you get that?
Yes, so.
And so with that said, it will then displace its own weight in the seawater, and that will cause it to float. Alright? So with that information, it means that it displaces its own weight, and then it will be able to float because now the upthrust is equal to the weight. Alright, so I'm going to write it out in words so you can see it. So should I use the entire yacht. So we're looking at the overall yacht now. So apart from the hull alone, we're looking at it from a bigger picture. So the overall yacht, the entire yacht, is not solid steel, right? So the entire yacht is not solid steel, but comprise what is comprise the word to use? Do you think comprise is the word to use? Comprise of other materials such as air, right? Such as air. Therefore, the overall density of the yacht is less than sea water. Alright. And remember, the density of seawater here is comparing 1025 grams per 1 meter cube. Right? So this is just 1 meter cube. But when you compare that now to the overall density of the seawater, which is more than 1 meter cube, then realize that the yacht itself will actually have less density when you compare overall. And so it follows that this means, connecting back to Archimedes' principle, this means that it will displace its own weight in sea water, causing it to float. Alright, so that's how you connect the density with Archimedes' principle. So you have to look at it from an overall perspective and not just for just 1 meter cube of the substance. Alright, any questions on this?
Can I explain again, please?
Alright, let me go one more time. So the question would have given us, right, the density of steel only, right? So they're saying that for every 1 meter cube of steel, you have 7,850 kilograms. So that's for every 1 meter cube. For the seawater, for every 1 meter cube of seawater, we found that density is 1025 kilogram per meter cube. So obviously these two things, one is greater than the other, right? When we look at it at this level, 1 meter cube and 1 meter cube of each. Now it says explain why the yacht. So now we're moving from specific to now a larger picture. So it's now moving from the hull and it's now talking about the yacht, which is the entire thing. So it says explain how the yacht is able to float in seawater, right? So how is it that it's able to float in seawater? First, if we look at the yacht as a body, it is not only comprised of steel. There are other things that the yacht is comprised of, because you have empty space in the yacht, right? It's not a solid that has no space. You can actually go inside the yacht. So there has to be some empty space inside there. So when we look at the entire composition of the yacht, on top of the water, you realize that it will have empty space, it will have steel, it will have other materials in it. And when we put together all the densities of all those things and compare it now to the amount of seawater that it's in. So we're not looking at 1 meter cube now of the seawater. We're looking now, comparing it now to the all of the seawater that it's sitting on. We realize that when we compare it overall, the density of the yacht is going to end up being less than the seawater that it's sitting in. You get that?
Yeah.
Do we get that?
That's there, but I read it.
Alright, so you can read it then. Alright, so let's calculate the volume of seawater displaced by the yacht as it floats. So how do we calculate the volume of seawater that is displaced?
Sir,
Mm-hmm.
is this the Archimedes principle or something like that?
to calculate the volume?
I'm not sure.
Come on, try
So would
again.
it be PVG?
PVG, what's that? Alright, Brit is on point. So Brit says we need to use density equal mass over volume. She said we need to use that. What are we trying to find in this?
The volume
Volume of what?
of CO.
That is what?
Displaced.
Alright, you see this information right here? That's gonna be the key to the explanation. That's gonna be the key to selecting the correct thing. So did you remember when I looked at Archimedes' principle and I told you that whatever amount of water that is displaced, right, is gonna be equal to the obtuse?
Yes, sir.
Right? And if this thing is floating, right, that means the obtuse and the weight is equal, correct?
Yes, sir.
And
Yes.
what when we look at so in essence, the mass of the displaced water is gonna be equal to whatever we had here up here for the yacht. So whatever amount of water that is displaced is going to be equal to the mass here of the yacht. And what they've asked us to find is the volume of the seawater that is displaced. So we know the mass of the yacht. And we know that in order for the yacht to float, it has to displace its mass in the water. So we can now conclude, right, that the mass of the seawater is going to be equal to 8,300 grams as well. Right? So the reason why we can conclude this is because the yacht itself is 8,300. You realize that? Alright. So if the yacht is 8,300 and the yacht must displace its own weight in water, that means the same amount of weight that is displaced is going to be the same amount of mass. So what we have done is equated them. Alright, so the mass of the yacht is equal to the mass of the water that is displaced. Alright, so now we can use this to find out the volume. So which one of the densities are we going to use here? Is it the mass of the yacht or mass of seawater?
Seawater.
Mass of the seawater.
Yeah.
Why would you use the yacht?
Because you said the mass of the weight displaced is the mass of the water displaced.
Alright. And what are we asked to find? The volume of what?
Oh, volume of seawater.
Right. So in that sense, we need to use the density for seawater then. Wouldn't that make more sense?
Yes, sir.
Alright. So the reason why we had to figure out what this is because we don't know what the mass of the displaced water is. That's why I said that it has to be equal to the mass of the yacht. Right? The mass of the displaced water has to be equal to the mass of the yacht. And we need the mass of the displaced water to calculate the volume. Right? So that's what that is for. But because it says seawater, we have to use the density. So whenever the unknown is in the denominator, right? What can we do with these two things? How would we find the volume?
Switch them.
So we can switch these, right?
Multiply.
Alright. So yes, you can multiply both sides by V, right? And then find V. But as I said, the quicker way to do it, once the unknown is in the denominator, you can switch these two quantities. Alright, so it's a shortcut, but you can do it to save time. Alright, so we have V is equal to mass divided by density.
Sir,
Mm-hmm.
good night. What if the unknown is in the numerator?
If the unknown is in the numerator, then you
Yes,
would
sir.
have to, I'm coming to that. Let me work it out first. So we have mass over density. So the mass is 8,300 kilograms divided. What was the mass of the seawater? Sorry, the density of seawater again? 1,025 kilogram per meter cube. So the volume is equal to what?
2.098.
How much?
8.1.
8.1.
1.
8.1. What's the unit?
Meters cubed.
Meter cube. And remember I said if you don't know the units, just cancel what is in the whatever is in the what? In the equation, and you will end up with the units. Alright, so this is meter cube. Whatever is left is your unit for the answer. Everybody got that?
Excuse me, sir.
Yes, go ahead.
Since this is being recorded, where will it be posted? I'd
It's-
like to rewatch it.
It's being streamed on YouTube. So you can go to the to my YouTube channel, the physics block, and you'll see it there.
Can you repeat the channel name, please?
The physics block. Somebody please text it in the chat. Alright, so somebody was asking, what if the unknown... Somebody was asking, what if the unknown is not in the denominator? What would we do? You would follow the simple rules of mathematics. So let's say, sidebar, we want to find the mass. And we have the volume. We already know the volume and we already know the density, right? So we know this and we know this. Somebody is asking, what should we do to find what is in the numerator? What should we do, class?
You're multiplying.
Multiply. What do I do? Alright, so you use math, right? So you multiply each side, whatever the volume is doing, you're doing the opposite of it. So volume is dividing, so in order to get rid of it, you multiply. So you multiply this side by V, and you do the same thing over here. So that cancels out that cancels out that. So the mass would be equal to the density times the volume.
Sir, could you cross multiply as well to get it?
You could also cross multiply. If you cross multiply, it's the same thing, because this will be multiplying this, which will end up with this, and then m is just multiplying 1, right? And you end up with this. Same thing. Do we get that?
Yes, sir.
Alright, somebody said if we can use a triangle. Yes, you can, but that I see that as something that's too... It takes away from the math of it. Alright? So use up your math knowledge. If the triangle works for you, then fine. But use up your math knowledge. Alright, so that's 15 marks for... What did we just do?
Sir, I have a question about the
Pressure.
the volume of the water displaced. Didn't we just calculated the density?
No, it gave us the density.
Oh, it's
What?
me right here, sir.
What we
My
did was to find the volume. So we know what this is and we know what this is.
Yes, sir.
Alright. Any other questions? Alright, let's move on to the next topic. So we have covered Moments, we've covered pressure. What's the next topic?
Waves, please.
Waves. Let's see what's going on waves. Right. So for waves, I don't remember what year this was. So forgive me. But this is question 5. Says define the term longitudinal waves.
Longitudinal waves are waves that has a vibration that is parallel to the direction of propagation.
Alright, very good. So if you remember sound waves, you remember longitudinal waves. So longitudinal waves, they operate like that, right? And remember, for longitudinal wave, you have regions of high pressure and regions of low pressure. Alright. So wherever you see I have them close together, that's regions of high pressure. We refer to those as what again? Start with a C.
Compression.
Yes. Very good. Come on the firing, man. Compression. So this is a compression. And regions of low pressure, what are they referred to? Refraction. So you have refraction. So you see that there is a pattern to this. So compression, refraction. And so we can also represent this longitudinal wave on a graph, right? And it will produce something similar to transverse waves, right? So you will get something like that, which is representing the areas of compression, high areas of compression, and the low areas will represent the refractions. Alright? Yes, crests and troughs. So we're talking about longitudinal waves. So the definition of longitudinal waves. So a longitudinal wave is one with vibrations. One with, of course you'd put this in a sentence. One with vibrations that are, what's the word? Parallel to the direction of what?
Travel waves.
Of propagation, or you say movement. So direction of propagation.
Can we just say wave, or we have to put that?
You have to put propagation or movement.
There's the particle
Okay, sir, thank you.
Yes. We get that?
Yes, sir.
Alright, so that's the 2 marks. So once you say that it has vibrations that are parallel to the direction of propagation or movement, you get your 2 marks, just like that. Alright, next part. So we have a figure here, which is the points of K, S, and what's this? A and D are shown. Alright, what are we to do here? Write 2 letters whose distance between them on the wave train in figure 4 represents the amplitude. So let's do this quickly.
L and A.
L and A. So is this an amplitude?
Yes, sir.
Yes, very good. So we have L and A, so that's A and L. Wavelength, 2 letters.
O and
A and O.
N and R. O and Q.
Alright.
A and C.
Alright. So let's go with, somebody said K and O. So let's look at K and O. So this is K, right? And this is O. And if you remember the definition for wavelength, what's the definition of a wavelength again?
The distance between 2 troughs or crests.
The distance between 2 troughs and crests. But what if it's not a trough or a crest?
Or the distance between 2 identical points on a wavefront.
Alright.
So it's how long it takes for refer to oscillate.
No, that's not wavelength. Wavelength is a measure of distance.
The distance between two successive points.
Yes, very good. So successive, that's the word that I was looking for. Two successive points, and you can also use two identical points. But the safer one to use is successive. So if I take the distance between this point at K, right, and I go back to the same point, right, there, then that is what we refer to as the wavelength. The distance between two successive points, or as somebody else said, if I should pick two crests, those two crests are two successive points. They are doing the same thing at the same point, right? So if I take the distance between the two crests, I also get the wavelength. If I take it between K and O, I also get the wavelength. Yes?
So you'd say the distance between two successive points on a wavefront?
On a wavefront or wave train. Yeah.
On a wave train.
So you can use wavefront or wave train, alright? Or you can say on a wave. Alright, so we have L. Do we agree that we can use L and P? What am I doing? L and P, or we can use K and O. You agree with that?
Yes, sir.
Alright.
Yes, sir.
What's another two letter that we could use for the amplitude?
CNP.
CNP. Alright, yes. What about B and N?
Yes, sir.
Could you use B and N as the amplitude as well?
Yes, sir.
What's the difference between this amplitude and the other amplitude?
One is a crescent.
In terms of the size or the direction.
One is positive and one is negative.
Right. So one is a positive maximum and the other one is a negative maximum. Alright. So moving on. State two differences between light waves and sound waves.
Light wave
travels faster.
Alright.
Travels when sound waves do not.
Very good. So number one, light waves move faster to sound.
Either one needs a medium and one doesn't.
Yes, you could say that as well.
Sure, we could say one is a longitude and one is a transverse wave.
Yes, you can say that as well. Sound waves move slower. Two. Light waves are transverse, so these are transverse waves. And what am I doing over here? So this is one. This is one difference, and this is the second difference. These are longitudinal. Alright, so, and of course you can say one light waves travel in a vacuum as while sound waves require a medium. Right? So any of those differences, you can state them and get the 2 marks. Very good. That's the end of that. Somebody said I should go through radioactivity.
Yes, sir.
So the time is going, so radioactivity. Let's do radioactivity.
Sir, I'm asking if
What was that?
I'm asking if there's time, if you could squeeze in optics after you finish.
If we have time, sure. Alright, let's do this question. It says here that in 20 days, the activity of a sample of bismuth decreases to 1/16 of its original value. Decreases to 1/16 of its original activity. Define the term half-life. Yes. Hold on. Somebody hand is up. Jade?
The time it takes for half of a radioactive substance to decay, or the nucleus of a radioactive substance
to decay. Alright. Decay by what?
Half its value.
Emissions.
By half. You have to include that. Half. Decay by half its value. You can just say decay, okay? Get that?
Yes, sir.
Alright. Somebody in chat says half its time. What? Half its time taken for the sample decay. Half-life is the time taken for a sample to decay. You're missing something there. You need to include that the time to decay by half its original value.
Sir, could it be the time it takes for half of the same same element decay?
Alright, is it just any element?
No, sir.
Alright, what type of element it has to be?
It has to be radioactive.
Alright, so this has to be a radioisotope or radioactive. So here it is. So the half-life of a radioisotope is the time taken. So these are the key things you need to include in your definition. It is a measure of the time taken for a mass or activity. So it could be that it's the mass that's decreasing, or it could be that it's the activity. Do you notice that in the question it says activity?
Yes, sir.
So it's not only about the mass, it also speaks to the activity. So the time taken for a mass or activity of a sample to decay, yes, you have that in there, but what is the other half? It says by half its original value. Do you see that?
Yes, sir.
You must have all these components to get it correct. Okay? And you must mention that it has to be a radioisotope, okay? And somebody said here, Daniela said the radioactive nuclei. So that can work too. Alright. Next part of the question. Yes, sir, go ahead.
Don't you have to include in a definition that it randomly decays?
That it randomly decays? Well, once you say radioisotope, it implies that.
Could a random decay, would it be for radioactivity, sir?
Yes, that's when you're defining radioactivity. That's why I'm saying to him that once you mention that it's a radioisotope, it would imply that it decays randomly.
Okay, sir.
Okay. Alright. Calculate the half-life of the bismuth. So how do we calculate the half-life here? So it says that it takes 20 days for the activity of the sample to decrease to 1/16. So is 1/16 the starting or the ending?
The ending.
Ending.
Some people say ending, some people say starting. Which is it?
Starting.
So let's read the question again. It says in 20 days the activity of the sample decreases to.
Or ending.
So it has to be the ending. Very good. So that means the starting would be what number? If the ending is 1/16, what's the starting? We're dealing with fractions here. 1. Very good. So if we are to calculate this now, right, going down here, follow the calculation here. So we would start at 1 because that would be the start, right? So this is the start here. And we should end at 16, right? And remember, all this takes 20 days to happen. We agree with that?
Yes, sir.
Alright, so let me erase this and do it over. So he asks us to find the half-life, right? So we're starting at 1, right? And we must decay down to 116. So let's go. So half of 1 is?
Sir, before doing that, sir, need to
Yes.
divide 20 by 4.
No, you don't need to do that. How did you get the 4? Where did the 4 come from?
Sir, sir, don't you need to see how many
Half-lives?
Yes, sir.
That's what we're doing now. That's why we are finding the half each time.
Okay.
Alright. So from 1, we find half of that, we get a half. Half of a half is a what?
Quarter.
A quarter. And half of a quarter is?
1/8.
1/8. And half of 1/8 is?
116.
Should we go any further?
No, sir.
Alright. How many half-lives did we go through a while ago?
4.
So it's 1, 2, 3, 4. So we just went through 4 half-lives, but the question is asking us to find out the value for 1 half-life. Now, if the entire thing took 20 days, so this entire thing took 20 days, right? What's the value for 1 half-life? So 1, so T a half. So T a half would be equal to how much? How would we find the value? Or the time taken for 1?
Divide the amount of half-lives by the total days.
Okay, so it would be the total days and you divide it by the number of half-lives that you got. And so the answer would be 5. 5 what? 5 minutes, 5 hours, 5 what?
5 days.
5 days. So in essence, what this is saying is that it takes 5 days, right, to decay from the original value to half. So each time it decreases by half, it takes 5 days to do so. Everybody get that?
Yes, sir.
Alright, so remember half-life. Remember half-life is a measure of the time it takes for some sample to decrease to half its initial value. And every time we decrease this by a half, that means it took 5 days. Every time I decrease it, 5 more days. I decrease it again, 5 more days. I decrease it again, 5 more days. And then we finish. So in total, we take 20 days. But actually, 1 half-life is 5 days. Alright. Next part of the question. Radioisotopes have many useful applications, but overexposure is a health hazard. State 2 useful applications of radioisotopes and 2 precautions to be taken when handling radioisotopes.
Cancer treatment.
So we can use them to do cancer treatment, yes. Carbon dating, yes, correct. I didn't hear that one.
And use as pacemakers.
Pacemakers.
Detecting cancer.
Oh.
The energy source in pacemakers.
Oh, okay. And then we have somebody said in the chat, we can use it for radiotherapy. That's the same thing about removing the tumors. We can use it for energy production. Somebody said that, yeah. Alright, very good. So the 2 that I had here was these 2. So I had radiocarbon dating, which is when we use the carbon-14 to calculate the age of a specimen. So whatever amount of carbon-14 that is in the specimen, we can use it to determine how old it is. Alright. Then we have external beam therapy. That is what they were speaking about when they said to remove cancerous things. So to be more specific, external beam therapy involves gamma radiation from cobalt 60 that is used to destroy cancerous tumors. And we can only use this form of therapy when the cancer is localized, meaning it has to be in one area. Alright? So those are two uses along with those that you mentioned. Alright, handling now. So somebody said when handling you must use forceps and store in lead. Okay. Anybody else? What other precautions should we take?
Why do you store in lead?
So remember, lead prevents, it is able to stop the absorption of the radioactive isotope. So it reduces the amount of radiation coming to you. That's the purpose of the lead.
So you said a precaution, right?
Yes, a precaution. So what would you do to prevent being exposed to high, what did you say? Being exposed to overexposure. What do you do to prevent overexposure?
Use protective gears and not touch it with your bare hands.
Use protective gear and not touch it with your bare hands. You have to be more specific than that. So let's be more specific. So, precaution.
Protective equipment.
Come again? What was that one?
Wear protective equipment.
Protective equipment. Alright. So here's what I have. So number one, you use appropriate shielding. So that protective equipment is referred to as shielding, right? And the shielding could be made of lead, right? And for gamma rays, and you can use lead for gamma rays, and you can use plastic for beta particles. So the penetration of gamma rays are high. That's why you use lead. The penetrating power of gamma rays are high, so you use lead. However, for beta particles, it's not as high as lead, so you can use plastic. Is that clear?
Yes, sir.
All right.
Yes, sir.
So using this measure, the shielding measure, it limits the amount that you will absorb as the person dealing with it. All right. The next thing is that we must minimize the time that you're near the radioactive source. So if you are around radioactive sources for extended period of time, it can be dangerous or even fatal. So a precaution is to do what you're doing in a very short time to limit the time you spend around these things. All right? Everybody's clear on that?
Yes, sir.
All right.
Yes, sir.
All right. So those are just the theory part of radioactivity. So we've done A, we have done B, now we're at C, the fun part. All right. So it says here, during the fission of 1 kilogram of uranium, and this word here is very important. Anybody can tell me what fission is?
When they like join together, splitting off two nuclei.
So is it splitting or is it joining?
Splitting.
It's splitting. So with fission, so remember, fission, split. Fusion, join. Fusion, bringing together. Fission, splitting. Is that clear? Somebody type that in the chat. Fission, splitting. Fusion, joining. Alright. So during the fission of 1 kilogram of uranium-235, 6.7 times 10 to the 10 joules of energy is released, and there is a change in mass. Calculate the new mass. How would we do this? Alright, somebody recite the formula for me. E equal, is it M or is it changing M? Is it M or is it change in M? So it's actually change in E,
delta M,
change in M times what?
C squared.
C squared. Alright, what are we given in the question?
Energy.
Alright, we know the energy, right?
Energy.
We know what C is?
Yes, sir.
We know what C is. So it's easy to find the answer now, right? So how do we find the answer? So you could transpose the formula itself first, or you could plug in the things first and then transpose. So for me, I prefer to transpose the formula first. So in order to get the new mass by itself, what should we do with the C squared?
Divide both sides.
Divide both sides by C squared. Very good. So that means this cancels out that cancels out that. That means the change in mass is equal to the change in energy over C squared. And then you just substitute now. So the change in mass is equal to the energy that was 6.7 times 10 to the 10 joules, all divided by C squared. So that's 3 times 10 to the 8 bracket. So meters per second, and then square all of that. So for those who are using the calculator, you need to put in the brackets there. Alright, so changing them is equal to what? So put that in a calculator. I was trying to find what my calculator is. Somebody do that and let me know. Somebody said, what does C represent, class?
Speed of light.
The speed of light. So this.
I got 7.44 multiplied by 10 to the power of -7.
Alright. Just give me a second. Let me look for my calculator. I really want to calculate it with you. Alright, I found it. Alright, so let's go to the show with my calculator. Alright, everybody can see my calculator?
Yes, sir.
Alright, you see the brand?
Yes, sir. We see brand.
Alright. Alright, so we need to enter. We need to enter 6.7 times 10 to the 10. So 6.7 times 10 to the 10. Right. Divided by open bracket 3.0 times 10 to the 8. That's the speed of light. Close bracket. Square that. Let's see what we get. Alright, what did I do wrong here? Maybe I need to put something else in bracket. Let's try this. Oh, my bad. So 6.7 times 10 to the 10. Alright, close bracket divided by open bracket 3.0 times 10 to the 8th, close bracket, square that, getting an incorrect answer.
So try using the button down there that says times.
The exponent button?
Yes, sir.
Alright, let's try that. 6.7 exponent. What's the exponent? 10?
Yes, sir.
Not working. Alright, so that
You wouldn't type 10, you just put the power.
Alright, I'm gonna do everything. I'm gonna do everything. So 6.7 times 10 to the 10 close bracket divided by 3.0 times 10 to the 8 times 3.0 times 10 to the 8. Alright, so I'm gonna change my calculator. Give me a second, let me change this. Another one that I use. What calculator are you using? And you put it, how did you put it in like that?
Sir, I never break it because it's your mode. Well, I can't get the answer.
Alright, guess what? Yeah, dash with this. Dash with this. Use an upgraded one now. Alright. So let's try this now. See what this does. 6.7 times 10. Alright, that's correct, right? Divided by
Yes.
what are we dividing? 3.0 exponent 8. I'm going to square that. Alright, that's the value that you get?
Yes, sir. 7.4 times 10 to the negative 7.
Alright, so if we should change this to standard form, what would it be?
So 0.4 times 10 to the negative 7.
Alright. Is that what everybody got? The Casio people, that's what you got?
Sir. Yes, sir.
Alright.
Yes, sir. Somebody say no in the chat.
What did they get? So you have to put it in correctly, you know. So use up your brackets. So what was the answer again? 7.4? Wait, let me see. Which year was this again? 2014? 2014. Alright, so I'm fact checking myself. What question was it? Question 6?
Sir.
Question 6. Alright, yeah, so we were correct. That's the exact same thing that I got when I did my answer sheet. So it's 7.4 times 10 to the negative 7. What's the unit for change in mass? What's the unit for the change in mass? Hello? What's the unit for mass, people? What's the unit for mass? Kilogram. So why are we stuttering? What's happening?
Sir.
Lock in, man. Lock in. Let's lock in. All right. So that is the change in mass. right? So what is the new mass? Given that the initial thing was 1 kilogram. So the initial thing was 1 kilogram. The change in mass is 7.4. What is the new mass? Anybody can tell me?
Repeat the question, sir.
So remember, they asked us to calculate the new mass. What we calculated here was the change in mass.
Oh, so is it gonna be what we just calculated minus 1 kilogram?
Yes, very good. Very good. So the new mass, right, is gonna be equal to the initial mass minus 7.4 times 10 to the minus 7. So the new mass is what? Put that in the calculator. So 1, okay. Alright, let's do that. So 1 minus the answer.
0.99. I got 9.99.
Alright. What's that in standard units?
9.9
Times 10.
9.9 times 10 to the negative 1.
Exactly.
0 times 10 to the negative 1.
9.0, 1.0. I'm hearing different
I
things.
said 1.0.
It wouldn't be 1.0 if you round it off. What's gonna happen if you run it off? You're gonna get back the initial value. So you can't run it off. So with these radioactive numbers, please don't round them off. Right? You put them to the standard scientific notation, or if you're working them out with the numbers, you keep at least 4 decimal places. The moment you run it off, your accuracy is out the window. Alright, so for this number minus from 1 is actually 0.99. What was the next one? 0.9999 go straight out. So guess what? I'm gonna write it in .99999 recurring. So this is recurring, and this is kilogram. All right. Body see that?
Yes, sir.
All right.
Yes,
So
sir.
that's how we do that.
Sir, I'm getting 2 points on
You getting what?
2 point something.
When you subtract these values?
Yes, sir. I think I see my problem.
Okay. All right. Let's see if there's another question. Definitely.
Wait. I'm sorry. What you just put, that's not in scientific notation.
No, it's not scientific notation. It's regular numbers.
Oh.
It's not scientific.
Okay.
All right.
Does it matter if mine is in scientific notation?
You will get the answer correct if it is in scientific
Alright.
notation. It's the same thing as the regular number.
Alright.
All right. So here is a bigger question now on radioactivity, 2013. So seems that they attempted to murder these people. All right. So 2013 question 6. Describe an experiment that compares the range of what's this representing?
Beta.
All right. So this is beta. Beta what?
Emissions.
Beta emissions or beta particles. In this case, it's emissions. And this is what?
Gamma.
And gamma emissions in what?
Aluminum.
In aluminum. So there are a couple experiments that we can use when we are trying to detect the beta, gamma, or alpha emissions. Now, the fact that it says in aluminum, can you remember which of the tests can be used to explain or to test for beta or gamma emissions?
The Geiger-Muller one.
The Geiger-Muller test, yes. We call that the absorption test. Very good. Very good, Brit. Which other tests do we have? Apart from these, the absorption test, can you remember name other tests that we can use? Anybody? Which other tests can we use to detect emissions of radiations? So we have the electric field test, yes. You have the cloud chamber test, very good. Yes, you have to remember these stuff, you know. What else?
Magnetic field.
The magnetic field test. Right. So there are a variety of tests, right? It's good for you to know them because you don't know which one they will question you on. But the fact that they said that it's aluminum, we know that it's the absorption test that we're going to use. So let's look at it. So for the absorption test for the aluminum, right, you're going to have your GM detector, right? That's the same thing that we were referring to a while ago. You're going to have your source in the container, right? And you're going to have the aluminum, right? So when the source emits a beta or gamma emission, what should we expect to happen with the aluminum?
The emission will pass through it.
Which one will pass through, beta or gamma?
Gamma.
Alright, so remember I said to you that gamma has the most penetrating, right? Because it is actually a wave, right? While beta is not as...
the most penetrating because it has no charge right there.
Gamma, yes, it also has no charge, but the main reason is because gamma is a wave. So gamma radiations or emissions are waves, but beta emissions, right? Beta emissions are actually particles, right? So if it is that the source is emitting a radiation and it is passing through and it is detected by the detector, it means that it has to be what? Gamma or beta. If it passed through and it is detected, is it gamma or beta?
Gamma.
It's gamma because gamma is the most penetrating, right? However, if it is, we don't know, you know, but if it is that we do the test and the emission does not go through, it's not detected, right? What kind of emission is that?
Beta.
Alright, so it will be beta emissions, right? So it would detect some things and then it will go back down to the background radiation, right? But the fact is that eventually it will not detect anything. So let's look at the method. So they ask us to describe. That's the 6 marks. That's where the 6 marks comes in, right? So it's good to have the diagram. The diagram will help you to describe it. So first, number 1, the method. This is what you're going to write for your 6 marks now. So number 1, we're going to measure the background count rate. Why is that so important?
Because they emit the radiation like regardless of.
Alright. Where does background radiation come from? Start with an E.
The emission.
Where does background radiation come from? So
someone in the chat said the environment.
The environment, very good. So remember, you know, you have this source here, right? But remember, it's this detector is also in the environment, so there are other emissions, background emissions that can go in the detector, right? That are not from the source. So first you need to take out the source and measure the background radiation which is coming from the environment. So the natural environment emits radiation. We call that background radiation. Is that clear?
Yes, sir.
Alright. Now, after we measure the background radiation or the count rate, because we call it the background count rate, we're going to now place a thin sheet of aluminum between the source and the detector to measure the count rate. So that's why we put the aluminum source, the aluminum foil here, right, in between the detector and the source. So that's the next step. After we have done that, we can now see what happens with the experiment. So if the count rate reduces to the background count rate, right, this means it is an alpha, well, in this case it would be beta. So I should have beta here. It would be a beta emission, right? If the count rate is unaffected. Oh wait, what did I do wrong here? Somebody tell me what I did wrong. What I have wrong here.
So other?
What should be if the count rate reduces to the background count rate?
A gamma emission, not beta.
Alright, very good, sir. So it would be actually a gamma emission, right? And if the count rate is unaffected, meaning that it doesn't pass through to affect the Geiger meter, right? That means it is a beta emission. Do we get that?
Yes, sir.
Alright. So if it is a gamma wave, it's gonna go through, it's gonna cause some radiation to take place, some count rate is gonna go up, but eventually it will come down back to its original value after the decay finish. If it is a beta emission, this aluminum foil will block it, so it will not go through and nothing will pick up on the GM detector. Alright, so that's how you explain that. Are we all clear on that?
Sir, can you go down? Let me take a picture.
Okay, let me. There you go.
I got it. Thank you.
Alright. So, next part of the question. It says here that we have liquid fluoride thorium reactor. It's said to be the new green nuclear reactor. Rewrite the nuclear sequence to show how the thorium-232 becomes uranium-233 and nuclear fuel by calculating the numerical values for X, Y, U, V, and Z. Alright, so basically what they're asking us to do here is to balance the equations. So for those who do chemistry, this should be a breeze for you. Right?
Oh, sorry, I was reading.
Alright, so remember now we are trying to find out what X and Y is for the first one. So we're working with the first one here, number 1. So we are going to rewrite this. So we have a neutron which has no charge that is going to be shot at the thorium. So it's going to be shot at the thorium, right, and it's going to cause it to decay into the isotope, an isotope of the thorium. So when it decays, right, the numbers that we get over here must be equal to the total over here, right? So if you look at these values at the bottom, right, when we add these together, what do we get for thorium for Y?
90.
So we get 90, right? When we add these together, what do we get for here?
233.
233. Is that consistent with what we are trying to achieve right here?
Yes, sir.
So first, so we want it to go from thorium here to 233 here. And then, next part, we're doing this too. So this is now going to decay. Thorium 233 is going to decay. And it's going to produce an beta emission plus this is an element. I don't know that element, but what we need to find out is U and V. So how do we balance this equation? So I want to find U and V. How we balance this? So 90 and this. So when you add this with this, you must get back 90. What number do we add to -1 to get back 90? 90? 91. Okay, 91. So 91. And what would be the top?
233.
And this will be 233. Alright. What's next? So we have number 3 now, balancing this one. So it's now 233 and 91, right? And we want to get it back into electron -1 plus uranium 233, right? So the top part already balanced out. And what do we need to get back the 91?
92.
92. Alright. Easy, don't?
Yes, sir.
So you're just doing some chemistry. Alright, so we've rewrite this. This is just 5. This is all of this. What we just do is 5 marks. 5 easy marks. And if you weren't sure about what you did, look right here in the next part of the question. Do you see that you can confirm your answer? Alright. So let's focus on this part of it now. So the next part of the question says this is the equation that represents the fission of uranium-233. What does fission mean again?
Break apart.
Splitting, right? Splitting. We're splitting the nucleus. So remember, I'll show you what fission is. So this was the working out. Fission. Where is it? I drew it somewhere. It's not in this one. Okay. So remember, fission is, let me draw it over here. You have a heavy radioactive substance, right? And we split it into 2 other identical, right? So that this is what we call fission. We're splitting the nucleus of a heavy radioactive element in order to get 2 other. Is that clear?
Yes, sir. Can it be 2 or more?
It could be 2 or more, but it also will result in a release of energy, right? And we call this the binding energy. So when they split, it's gonna release energy, because remember the nucleus there, it's bind together with the strong force, right? The strong force. So when you try to split this heavy nucleus, it's gonna release the energy that was used to bind it, and it's gonna produce 2 other, we call the daughters. All right. So let's go back to this now. So as you can see here, this here, so they shoot the neutron at the nucleus of the uranium-233, and it decays into what? So we have 1 here, 2 here, but it also releases other neutrons that will cause a chain reaction. All right, so these other 3 that are released are going to go and hit the nucleus of other things, and it's going to cause a chain reaction. Right? And at the end of everything, we get energy. Everybody understand that?
Yes, sir.
Yes, sir.
So these are referred to as the products. On the right hand side, those are the products, right? And on the left hand side, those are the raw materials. Alright? So what are we asked to do here now? So we are given a table. Alright? We are given the atomic mass of each of these things represented in the equation. So we are given the atomic mass for uranium. Anybody knows what SB means? Which element is that? See if there are any chemistry geniuses in here. Anybody knows what SB is?
Sir, that's transition.
Alright, so these are way down. 150, what is 51? You're not gonna know those. But what is important? Right. What is important is the atomic mass. Alright? So the atomic mass for this is 233 point ... U. For SB, it's that. So each of these have their own atomic mass, and it is measured in U. Right? And that is just a unit that we use to measure very, very small masses. Right? So instead of using kilogram, right, we use U, which is more convenient. But here it tells you that 1 U represents how much kilograms?
1.66 times 10 to the negative 27.
Alright, and remember, if we're supposed to use Einstein equation, we cannot use U back in the equation, you know. What we have to use?
Say kilograms.
We have to use kilograms. So that is why you're given the conversion factor. Alright, so let's move on. So it says here we are to calculate the energy released in the fission reaction, right? So we are trying to find out the energy that is released. That is this right here. Do we see that?
Yes, sir.
This is what we are trying to find out. So the question is, how are we going to find out the energy that is released?
Sir, you add up the energy on the product and reactant side.
So
And then subtract them.
are these energies or masses?
Masses.
All right. So remember Einstein equation, E equal mc squared, tells us the relationship between energy and mass. And what we have realized is that the change in mass is equivalent to the energy, right? Given that C remains constant. And we know that C is constant, the speed of light. So what Einstein discovered is that we are able to convert mass into energy. Right? So if we know what the mass is, we can figure out what the energy is. Do we all see that?
Yes, sir.
Alright, so our objective now is to figure out, we're going to replace this energy and we're going to try and find out what the change in mass is. Because we know we can use them interchangeably because of this equation. So our objective is to find out the change in mass. So we need to, as they said, add up all of these, right? That's what you said. And we're going to subtract it from over here. That's what you said? Is that what the person said?
Yes, sir.
Alright, so let's do it down here now. So I already started it. So what we know is that because of the law of conservation of energy, we know that energy cannot be created or destroyed, correct? We agree?
Yes, sir.
So that means whatever amount of mass or energy is on this side of the equation must be equal to whatever is on the other side of the equation. right? And so what we're going to do now, we're going to take each of these elements and we're going to write down the atomic mass. So we have the atomic mass of this, the atomic mass of that, we have the atomic mass of this, we have the atomic mass of this, and we have the atomic mass of the neutron. And we don't know what the energy is, but we know that the energy is equivalent to the change in mass. So that is going to be our unknown. Everybody follow that so far?
Yes, sir.
Alright, so this now, once you pass this stage, it's just a matter of mathematics. So let us add these together. So when you add these two together, what do we get?
Sir, I got 234.048331.
Alright, so 234.
34.04.
0.04.
I got 0.40.
0.40. So which is it? Which is it? Alright, let me try it again.
0.04, sir.
0.04.
Yes, sir.
Alright. So now I have to go work it out.
I double check.
Say what if you trust you?
Yes, sir.
Alright, trust. We trust in her. So 0.048, that's the correct thing?
Yes, sir.
What else is there? There's more than 3? I see 1, 2, 3, 4, 5. I see 5 decimal places. 31 equal. Alright. What's the total here? What's the total right here? Just put everything in the calculator. So remember, you have 3 neutrons here. So you're multiplying the mass of 1 by 3. And then you're going to add it to all of these.
Sir, I got 233.8585159.
Alright.
Someone step on me?
Yes, sir.
Alright, for the sake of those who are struggling, I'm going to be doing it on that side. So it's 132.91525 plus 97 what? 97.91033 plus it's gonna be 3 times 1.0087. Oh, it's 67. Alright, so that's everything. And the answer is, are we seeing the answer? That's what you got?
Yes, sir.
Yes, sir.
So 233.85159. So it's 233.85159. And you notice I'm keeping all the decimal places, very important. Okay? Plus change in M. What's next?
You are going to times it. Oh, sorry.
Times?
No, I'm ahead. I'm a step ahead.
Okay, very good. So we're gonna subtract 233.85159 from both sides. So when we do that, 233.85159, subtracting that from both sides, so this is gone. So what is the change in mass?
0. 0 point, yeah, 0.
I got 0.1967.
0.1967. That's it? 2?
Yes, sir.
That's it? Alright. Remember now the units for this is what? U. All of these were U. So that means this have to be U.
Yeah, so we're not about to use U again, right? It's KG.
Right. But remember all these that we just use in the equation, right, is U. That's what we end up with, right? We never use any kilogram in this equation here. All of them was U. So the answer has to be U. But now we're going to convert all of this into kilogram by doing what?
Multiplying it by 1.66.
Alright, very good. So we're going to multiply this now to get it into kilograms. We're going to multiply it by the factor that they gave us here, 1.66. 1.66 times 10 to the what?
Negative 27.
Negative 27, right? Kilograms. And that means our change in mass is going to be equal to
3.262.
3.26552. That's it? 3.5.
Yes, sir.
Right here? The 3 should be right here?
No, sir. 3.555.
Oh, my bad. You said 3. You said 3.5.
Number 5.
Alright, very good. That's it?
2 at the end. On the end.
Times 10 to
It's
the
not done.
28.
Times 10 to the?
Negative
28
kilograms.
Good. And what was our objective again?
To find energy.
The energy that is released. So now we can find the energy that is released, correct?
Yes, sir.
So the energy that is released is going to be equal to the change in mass times speed of light squared. So you put that in the calculator.
2.4
times speed of light, 3.0 times 10 to the 8, right? And that's meters per second, and this is kilograms, and that is squared. So what's the energy released?
2.9389968 times 10 to the negative 11.
Okay, I have to run back the last part if I'm please.
2.938
Mm-hmm.
99
68
times 10 to the negative 11.
negative 11. What's the unit?
Joule.
Alright.
Joule.
That energy they seem low. Alright, so let me confirm.
Let me get it on.
Then I get 9.7.
I get 9.7966656 times 10 to the negative 20.
Alright. So remember this is a nuclear reactor, you know. So the energy cannot be so low. So that means something is wrong with that calculation. Right? So by looking at your answer, you know. That's what you get as well? Alright.
There's something wrong with that.
Let's do it on the calculator. So let me put the screen over here so I can see the numbers. Nuclear reactor cannot release such a little bit amount of energy. Wouldn't make no sense to build it. Alright, so let's work it out on the calculator here. So 3.26555. Oh, too much 5. 5552. What did you use last time? Times
10 to the negative 28.
Negative 28. Right. And then we're gonna times that by what?
3 times 0.
0 times
Times
10 to the 8. And we're gonna square that.
Yes, sir.
And then close bracket. And it's the invalid answer. What did I do wrong?
Sir, the square.
Should I square the bracket or square outside? Still invalid.
Square? So we're not going to square it.
It has to be squared. It has to be squared. It says speed of light squared.
The 2.9 thing is correct.
Okay.
Correct.
Okay, let me see. 3.0.
But when we square it, I don't get that. I got 8.81.
Invalid answer.
What? Also, we get 2.93.
Use 9 times
What should I use?
10 to the power 16.
Oh,
Sir,
for this?
Use 9 times.
Okay, 9 times?
10 to the power of 16.
9 times 10. Power of what? 16?
Yes, sir.
Alright. Still invalid.
Sir, bracket it though, bracket.
I don't think this calculator can calculate that big number. It only gives it in can calculate that big number. Let's try this one. 3126 5552 times 10 to the it's negative 28, right?
Yes.
Oh my gosh, 3.2655552 negative sign negative 28. All right. This can't calculate it either. Alright, so I'm just gonna go with what you tell me, because my calculators aren't calculating. So what was the answer you got? So what you can do to make a job easier, just square this first, right? So in the next line you can square it. 552 times 10 to the minus 28 kilograms times, when you square this, what did you get? When you square the speed of light, what did you get? 9.0 times 10 to the
16.
Alright, meters per second. So when you put that in your calculator now, what is the answer? Everybody must can get this one.
Say 2.938.
38.
9968. Times 10 to the negative 11.
Okay, so that's that. Okay. Alright. Which year is this? 2013. Alright, so let me check now to see if that's what get for my answer. Just 2013.
All of that work now that's supposed to be about 10, 12 marks.
Let's find out. We've been on it for a while. So I think we have done extensively the radioactive topic. Right? It's 2013. Paper 2. What question was it? Question 6? Yes, so that's the actual value that is given. That's the actual value I got when I did it before now. Alright. So that is how much marks? How much marks is that?
4.
That's crazy. That's crazy. That's highway robbery. Alright. So most of the marks come from if I can describe the experiment.
Okay, interesting.
So guess what? This is gonna be the difference between the ones and the twos, you know. Some people go just do the first part, and then there's the other persons that gonna do B and C and get everything right.
Okay.
Alright, so when you're doing the question, make sure you do everything. Everything. Alright. Yes? Next topic.
Sir, I have problem with like focal length and it here.
Newton, somebody said Newton's law. Alright, Newton's law is quick. Newton's law is quick.
But sure.
Newton's law.
Say electric circuits after the.
I think everybody should know. Everybody should know this. This is not something I should be doing. Newton's 3 laws of motion. You should study that.
Which topic is this?
This is Newton's laws and momentum.
I know that.
So everybody should know this. Let's go to a calculation. Alright, so it says here in a car crash, a car traveling at a constant velocity of 26 meters per second crashes into a wall and is brought to rest. Calculate the initial momentum of the 70 kilogram test dummy in the car before the crash. So this is 2015. Alright, so how would you answer that?
A momentum form.
P equal mv.
Alright, so the momentum formula is P equal mv. And what are we trying to find here? The initial momentum, right? So I'm going to put I to represent the initial momentum. So that means we need the initial mass and we need the initial velocity. So the initial momentum is equal to, what's the initial mass? What's the initial mass? It's 70 kilograms, right? That's what he said right here, right? So 70 kilograms times what's the initial velocity?
26.
26. This is question 4. 26. So that is giving us meters per second. So that means the initial momentum is what?
1820.
1820. You sure about that?
Oh Jesus! Wait.
Let me check. I'm not saying you're wrong, I'm just asking if you're sure.
I got that also.
1000, alright. So we have confirmation. So this is 1820. What's the unit for momentum?
Kilogram meter per second.
Kilogram meters per second. Very good. Alright, so this is when it's going towards the wall. Notice the answer is positive, right? It's a positive answer because it's going forward. Alright. Now it says here we must calculate the average force exerted on the dummy by the seat belt during the crash if the duration of the collision is 0.1 seconds. So we are asked to calculate the average force. So via average. And we are given the time. So which formula you know have force, time and momentum in it? chat here. Alright, Daniela going on a roll. So for those who don't know the 3 laws, you put it in the chat. Thanks, Daniela. Anybody can answer this? What formula can we use to find, what formula has force, time, and momentum in it? It's one of Newton's laws. Which one of them has that inside it? Alright. Done. Nice. So, if you remember the formula, there are 2 ways we can represent the second law. So the second law, we can represent it using F equal m times a. But you notice we're not given enough acceleration, right? So we cannot use this to find the force, the average force. So we need to break up this. We know that, but what's acceleration equal to?
Change in velocity over time.
Alright, so change in velocity over
T.
Alright, so we go substitute this for a now. So we're gonna get F is equal to m what? V minus u all over t. Right? And so F is gonna be equal to, when you multiply out this bracket, what we get? mv mu. What is the difference between v and u here? What are we talking about?
One is initial and one is final.
Alright, very good. So v is final velocity, u is initial velocity, and then we divide it by time. So can we use this to find the answer for this question?
Yes.
We have all the variables, right? So the question says it takes a time of 0.1 second, right? So let's use this. So F is equal to the mass, which is 70 kilogram. And what is the initial, what's the final velocity again?
0.
It would be 0. Yes. Minus. Oh, let me write. We get points to write to our formula. So let me write about the formula. mv minus mu. So please remember to write your formulas. You get marks for writing a formula. So even if you don't know how to calculate it and you write the formula, you get the mark, 1 mark. Alright, so we have 70 kilogram times the final velocity, which somebody said 0. Why is it that we say 0? Why is the final velocity 0?
It says something about 26 to race.
Very good. See it here? See the giveaway here? So it starts at a constant velocity and it's brought to rest. Once it's brought to rest, it is 0. Everybody get that?
Yes, sir.
Alright. So it's brought to rest, so that means the final momentum is going to be 70 times 0, which is going to give us back 0. So 0 meters per second there. And all of this now is going to minus. What was the initial momentum we calculated up here?
26.
No. Initial momentum, I never say velocity. So initial momentum. So I don't need to calculate this again, right? So it's gonna be 1820 kilogram meters per second, and all of that is gonna be divided by what?
0.1.
0.1 seconds, right? And remember, once it is time, you always use seconds. So if this was in minutes, you convert it to seconds and you use it in the formula. Everybody get that?
Yes, sir.
Yes, sir.
Alright. So when this becomes 0, so this is going to become 0. So this divided by this, what is the answer?
1 into 100.
So it's gonna be minus, right? Because there's a minus there.
Yes.
Minus what?
18,200.
18,200. What's the unit for force? Average force. Newtons. Right. So if we were supposed to use this, it would be kilogram meters per second squared. Right? So kilogram meters per second squared is the same thing as this, which is equivalent to that. Everybody see that?
Yes.
Alright. So that's 3 marks there. Next part. With the removal of all protective features, the dummy was subjected to another test, another crash test with the same initial speed. This time it was subjected to a lethal deceleration force of 45,000 newtons. Calculate the duration of this collision. How do we do this? So let's look at what we're given. We're given this, right? What is this?
The force.
What kind of force? The decelerating force, right? So that means the F average now is not going to be this anymore, right? It's not going to be that. It's going to be what? It's going to be equal to 45,000 newtons, right? And it says we're to calculate the duration. So when you say duration, what are we trying to calculate? The time, right? Alright, so what we're going to use back again?
The same formula.
So it's going to be force is equal to the change in momentum, right? Which you already calculate up here. Where was it? Right here. So the change in momentum is this. Alright? So the change in momentum divided by T, right? And we're trying to find T. T is in the denominator. So what we need to do? Switch them around. So T is equal to the change in momentum over the force. Right? So T, so remember T cannot be negative now because it's time. So that means the change in momentum should be what? Looking at this calculation at the top here, what's the change in momentum? Negative
1,820.
Alright, so it's gonna be negative 1820 kilogram meters per second squared. That's what it is. No, kilometers per second. So that's that. Divided by the force, and it says the force is decelerating, so it's a decelerating force. So is it going to be positive or negative?
Negative.
So it's going to be negative. So it's going to be negative 45,000 newtons. Right? So we know that a positive divided by a negative divided by a negative give us a what?
Positive.
So negative divided by negative gives us a positive, and then when we divide this number by this number, what we get?
.0404.
Alright, so we get 0.04 seconds. Right?
Yes, sir.
Alright, that's it. So with Newton laws, you just have to remember these formulas here. So you have the first formula, whenever you get an acceleration, you can use the first formula. However, if you don't get an acceleration and you get the time, you know that you have to use this formula. At the time I get the velocities and the masses, can use this formula. When it comes on to momentum, remember that momentum, whether initial or final, is always equal to momentum of a body is m times v. That's momentum of a body. Alright? Are we good?
Yes, sir.
Yes, sir. Okay.
Alright. There was one person that said something about lens. Let's go to lens. Here's a lens question. 2015. Question 6, 2015. How would you do this question now?
Sorry, again, zoom up a bit.
Okay, coming up.
Sir, this is the last topic for tonight.
Yes, I would like to go to my bed, so I can leave you all to finish your studying.
Sir, we're not studying no more.
Alright, that means you finished study then. This was just to finish it off.
Yes, sir.
Alright, let's go. Lock in. Almost there.
Right.
So what are we supposed to do? It says copy the figure and draw the ray shown as it emerges on the other side of the lens and its relation to the focus. Show the principal axis and the focal length. So what kind of lens is this representing here? What type? We have two types.
Diverge.
So diverging, me here converging. Which is it?
Dive.
Alright, so it is a diverging lens, right? What's another name for diverging lens?
Concave.
Alright, somebody typed in the chat. Very good. So this is a concave, right? Alright, concave. So concave. So what we're gonna do is gonna replicate this down here. Alright. So you know that you're gonna need your geometry set in the exam, right? Alright, it's a poor drawing, but let's go. So it says you need to have the principal axis in it, right? So remember, the principal axis goes through the center and it is a horizontal line that goes through the center. That's your principal axis. It's not so straight. So
There, did you go up?
alright, so that's the principal axis. Right, we need to put in the ray diagram. So this is the ray. So the ray is gonna go through the lens, right? And then what happens when it goes through?
It goes up.
It's gonna diverge. So it's gonna bend away, right? And if we extrapolate this line, if you should project this line, the straight line backwards, what would happen? It would intersect the principal axis, correct? Am I correct? So let's change this. Are you still with me? Somebody have to answer.
Yes, sir.
Right, so remember it says that we need to show the principal axis and the focal length, right? So before we show the focal length, we need to establish our principal focus. So let me label this. So this is the principal axis. For those who don't know, principal axis. Right? And then if we extrapolate this line here, meaning that I extend it backwards using dotted lines, right? That means it's gonna meet the principal axis right here, and this is what we call the principal focus F. Right? So we call this the principal focus. Now the last thing we need to put in is the arrow here, and also it says the the focal length. What is the focal length again? What's the focal length?
Between the center and the F.
Very good. So the focal length is the distance. It's a measure of distance between the principal focus and the optical center. Right? So we put that in, and that is our focal length. We see that?
Yes, sir.
And if it was a convex lens, it would be the opposite. So the line here that goes out would be converging, right? So just to do a quick sketch, so if it was one of these, right, and the ray goes through, right, what would happen is that it would converge, and
sir, you have to know the different case scenarios.
yes, it's good to know them. Alright, so this is for a convex lens or a converging lens, and the principal focus will be right here.
So why is there a second line at the bottom?
Because I added a second ray. So let me put in. So this is a ray. So these are rays. Right? So these are rays. Right? So these represent rays of light. Right? While the middle line represents the principal. What's it called again? Principal axis. Don't forget that. I really hope this topic comes on the exam. Alright. Next question. Write in words or symbol the formula for magnification of an object. So you just roll that off quickly. So magnification is equal to what?
M equal V over U.
V over U. What does U stand for?
Image.
The image. Image what? It can be the image height or
distance.
Or the distance. Right? U stands for
Object
Height or distance.
object height or distance. So it's a write in words or symbol the formula for magnification. 1 mark. This now. So this is what you were asking about. So here it says an object AB. So this is the object AB. Is placed 20 centimeters in front of a converging lens. So if it's a converging lens, right, that means this. How do we represent a converging lens in using a line diagram? Is this a true representation of the converging lens?
No, sir.
Alright, what should we put on it to make it a converging lens?
The curve beam something.
No, that is when you're drawing a diagram like this. But what if it's not this? What if it's a line diagram like this one? So what we use is actually a triangle, right? So depending on what type of lens it is, we either set the triangle right side up or upside down. So we know that for a converging lens, right, the center is larger. So the lens is larger at the center, right? So that means the triangle would look like this. So that represents a converging lens. If it was diverging and it was a line diagram like this, it would look like this. So the diverging lens would look like that. Do you understand that?
Yes, sir.
So it's really, this is representing this right here. So if you follow the triangle, it's gonna go inward, then come out, inwards, then come out. For the converging lens now, it's gonna be the other way around. So this is gonna come outward. Alright. So the focal length F is 10 centimeters as shown in the diagram. What's the focal length again? Distance between what and what?
Between the focal point and the optical center.
Alright, very good. So distance between this and that. So they're saying that the focal length is equal to 10 centimeters. And it says the object is placed 20 centimeters in front of the lens, right? That means the distance of, right, from here to here is 20 centimeters, right? So that's what they're giving us. Now it says here, calculate the position of the image formed and state on what side of the lens it is located. What will we use to calculate this? So we get the object distance, which is, what's the letter for object distance again? U or V?
U.
So we use a U. We get the focal length, right? We get the focal length, which is, what's the symbol for focal length? It's a common F, right?
F. Yes, sir.
Alright. And they ask us to find out the position of the image that is formed and state which side of the lens. So they're basically asking us, so the position of the image is the image distance I. Not I, sorry, V. So which formula you know of common F, U, and V?
The one over U and the one over.
Alright, very good. So you see why it's important to identify the things in your question? So the formulas can come back to you easily. And for the person that asks about formula sheet, no, you will not get a formula sheet for physics.
So when they reach cheap, they give you a formula sheet or no?
No, they give you a sheet with constants. With the
That's
constants.
interesting. That's constant. Okay.
Yeah. They expect you to know it. So the focal length is 10 centimeters equal 1 over U. U was given to us, yes or no?
Yes, sir.
It is 20 centimeters plus 1 over V. Alright. So we're doing some. So we need to find 1 over V now, right? So 1 over V is going to be equal to 1 over 10 minus 1 over 20. Am I correct to say that? Is that correct?
So it would be possible to put 20 minus 1 over 10.
So remember these are plus, you know, at the top here. So if you want to get 1 over v by itself, we're gonna have to remove this positive and bring it on the other side, which is gonna make it a negative 1 over 20. Get that?
Yes, sir.
Alright, and then yeah, something else, go ahead.
Okay.
Alright, and then this is a matter of doing fractions now. So question 1 mathematics paper. So this is 20. So 10 into 20, 2 times 1 is 2, minus 20 into 20, 1. 1 times 1 is 1. So that means 1 over v is equal to 1 over 20. Alright, so what is v now? We're going to find v yet, and that is 1 over v.
V is equal to 20.
Alright, very good. So we're going to do is flip both sides. So the 1 over v equal 1 over 20. To find v, you just flip both sides. So v is equal to 20 centimeters. Got it?
Yes, sir. Yes, sir.
Alright, calculate the magnification of the image now. So we know magnification is m equal v over u. Is that it?
Yes, sir.
And then we found that v was already 20. And this is 20 centimeters. And this is also 20 centimeters. So the answer is 1. And this is another quantity in physics that does not have a unit. It has dimensions, but it doesn't have a unit. Alright. Is the image form real or virtual? Based on the answer.
Real.
It's real? How do you know it's real? You're correct, you know. Just tell me how you know.
Sir, because the value that you get is not negative.
It's not negative?
Sir, because it's showing on the other side.
Showing on the other side.
The lens.
Alright, so let me tell you what you need to remember for this. So you see this beautiful. Show you right. I'll put it right here. You see. You remember this?
Yes, sir.
So if the distance of the image from the lens is positive, right?
Sir, just what I was talking about.
It's gonna be real. Alright, so our answer is positive here. Do you see that?
Sir.
So if the answer is positive, that means it is a real image. Got it?
Yes, sir.
Alright. And that's the 15 marks. Oh, we're missing one thing. I think one of the questions asks us what side of the lens it is located.
Yes.
Would it be on the same side as the lens, or would it be on the opposite side of the lens?
Opposite?
Alright, how do you know that? You know I'm gonna ask that.
It's in between.
What tells you that it has to be on the opposite side?
The lens?
The lens, the type of lens that is used, right? So because it's a whatever lens we're working with here,
Concave.
it's a concave here in this question.
So it's a convex.
It's a convex. This is a convex. So converging is convex, right? And if it's a convex lens, remember I said that the image is formed where? See one convex lens here? So the rays are going to come at a point on the other side of the mirror, on the underside of the lens, right? Which means if the object is over here, right, the image is going to be formed on the opposite side. Everybody get that?
Yes, sir.
Yes, sir.
If it is a diverging lens and the object is over here, the image is going to be over here on the same side because of the diverging lens. Do we get that?
Yes, sir.
So the type of lens tells you the position of the image, and the value that you get for U and V tell you whether it is real or virtual. We good?
Yes, sir.
All right. And I think that is it for me. What's the time now?
After 11.
11:11. All right, so that's it for me. Any question before I go?
No, sir.
I wonder if
No, sir.
Dr. Brissett is still here.
Oh, sir, somebody was asking if the questions,
Mm-hmm.
but they answered if we might have access to them.
If the questions come again, I didn't get
Yes,
that.
sir, that would be.
Because they're asking if there's like a group or something that you could send the questions in, but it's being streamed on YouTube. You can just watch it there.
Right. So remember, let me put it up. Put it up.
Sir, question.
Mm-hmm.
What do we need to know about magnets and magnetism around?
For magnetism, so you need to know how magnets work. You need to know that you have opposite poles attract and the like poles repel.
When I say how magnets work, I thought there's something with the single magnet in the field, and then having north and south, you have to draw
The field lines. The
Yes,
field
sir.
lines, yes, all of that.
Sir, so it's when north and north, south and north, and south and south. Is it?
Let me show you quickly. So let's go to what they were saying, magnets. Alright, so for magnetism, remember you need to know the definition of a magnetic field. That is a region in which a body experiences a force due to magnetic polarities, and magnetic polarities means north and south. Alright, you should remember this. So when you have a north and a south, they are going to attract, and the field lines always go from north to south. So the arrow is pointing this way, right? So field lines always go from north to south. You get that?
Yes, sir.
Yes, sir.
So this is attraction. Over here, same thing is happening. You have a south and a north, and a south and a north, but the difference with this diagram over here and this diagram is that the magnets are side by side, right? So the force is going to be pulling towards each other this way, right? If they are like this, the force will cause them to go this way. So this follows Newton's third law. So this is attraction. So both of these are attraction. And notice the field lines, they do not overlap. And whenever the field lines are, so in between the north and the south pole, that is where you are going to have them being parallel, right? But as you go out further and further away, they become like that, like an elastic band.
Oh, yes, Yes, sir. And sir, they move away from the north and towards the south, right, sir?
So when you have a north and a north, right, you're gonna get this. So north and a north. So here you have a north and a north. They're gonna repel each other. So you notice that the forces are going opposite directions to each other.
Yes.
So this is repulsion. Same thing with them. If you put them side by side, you have a south and a north and a north. They're gonna repel each other, right? And so with this right here, you would not experience any force because there is repulsion. You get that?
Yes, sir.
Alright, then you need to know the tests that we can use to get magnetic fields. So if we have a magnet and we want to know the magnetic field lines, we can use the compass plotting test, right? And we can use the iron filings test to know the magnetic fields, to see the magnetic fields. Alright, remember that a uniform magnetic field exists in the central region between plane facing magnetic poles. So as I said, see two planes here. So planes will mean that this surface here and this surface here, those are two planes and they are facing each other. So notice with the two planes, these lines are parallel to each other. They are not touching each other and they are parallel. Do you see that?
Yes, sir.
But as you move away from these two planes, you notice that the field is now starting to bend. Right? Alright. Remember that Earth is also a magnet. Right? Our Earth acts as a magnet. That's why we have a North Pole and a South Pole. And your magnet, if you have an actual physical magnet, it will always align with the magnetic field of the Earth if you should suspend it from a string. Alright, and that's basically magnetism.
Okay, sir. Thank you for the class.
Alright, so for those who want to do electromagnetism, again, we have the videos on YouTube for that, and I believe I sent them in the group. So let me, I have to close it down now, and you need to get to sleep. So let me see. Right, so the videos that I sent in the group were what? I sent some videos in the group for AC. Let me check. You're all in the ministry group, right? We are all in the ministry group, right?
Yes, sir.
Yes, sir.
Right, so in the ministry group, it's not coming up on this.
Sir, it's over on the left hand side under the statue something.
Or the community and stuff, sir?
Yeah, no man,
below the icon.
Yeah, I'm looking for the. It's not there.
No, sir, below the icon, the statue. Sir, below it, sir.
Below it here?
Sir,
oh,
yes,
channel.
Yes,
oh,
sir, it's right here, sir.
I'm not smart, you know. I'm not smart. That's how I'm doing physics. Alright, so I'd sent them in the group here for AC generation. If I want to go back over, it's in the group. Oh, I think this is one of them. No, that's chemistry. Yes, see it here. So those persons who want to do back electromagnetism, this is a good video. Right, and also if you go on the channel, in my channel, you will see the one for DC motors. Alright, so I'm wishing you all the best in the exam tomorrow. Remember, stay confident, remember your formulas, remember your laws, and ensure that you approach a question as if they are like puzzles you're trying to figure out. So if you get a question, you always want to find out what you're given, right? You find out what you're given first, then you find out what you're trying to find out, and then you select the appropriate equation that will help you to solve the problem. Is that clear?
Yes, sir. Thank you, sir, for the class. It was amazing.
Alright, you're welcome.
Thank you, sir. Bye. Good night.
And for those who didn't subscribe yet, please subscribe to the channel. Have a good night.
Yes, it will start. It's the way.
Oh, you're up still?
Yes.
I thought you were sleeping.
Thank you, sir. You know, I fell asleep. I woke up back and you were still here with the students.
Yes, yes. Alright, so I'm going now.
Alright. All the smart students. That's it. I send the channel in the Alright. Bye.
Bye.
So you can close up.
Recording stopped.